জয়েন করবেন।
ঠিক আছে।
কিরকম রেসপন্স পাচ্ছ সেমিনারে?
ট্রিমেন্ডাস।
তাই? হ্যাঁ, খুব ভালো।
মোর দ্যান 1500 আমাদের রেজিস্টার্ড।
মোর দ্যান 15 না, 1777 এখনো পর্যন্ত আমি মেল পাঠিয়েছি রোজ, আর 1780 আর 2300 থেকে মানে 2300 থেকে মানে 2300 জন দেখছে আর কি ইউটিউবে।
খুব ভালো।
ফিলিপাইন্স, বাংলাদেশ, ইউকে, ইউএসএ, কানাডা
সকলেই তো অ্যাক্সেস করতে পারছে, সুতরাং সাবজেক্টে ইন্টারেস্ট থাকে তারা তো জয়েন করবে।
হ্যাঁ, মানে মানে সব রকমের আছেন, মানে ফুড সায়েন্স, ফুড টেকনোলজি, নিউট্রিশন, হোম সায়েন্স, মানে মানে মাইক্রোবায়োলজি, মাল্টিডিসিপ্লিনারি সাবজেক্টস থেকে আসছে, ফিজিওলজি অবশ্যই।
বুঝতে পারছি। হ্যাঁ, বিকজ দিস ইজ আ মাল্টিডিসিপ্লিনারি এরিয়া, তাই তো? ফলে অনেকেই আসতে পারে।
হ্যাঁ, সেটাই।
আচ্ছা, লিভ করতে গেলে কি করতে হবে আমি জেনে রাখি। এই তোমরা শুনতে পাচ্ছ কি বললাম?
হ্যাঁ ম্যাম, শুনতে পাচ্ছি আপনাকে। হ্যাঁ বলুন আপনার কোয়েশ্চেনটা আরেকবার।
ও আচ্ছা, দেবাঞ্জনা।
হ্যাঁ ম্যাম, দেবাঞ্জনা।
হ্যাঁ, শোনো না, আমি যখন যদি ধরো মাঝখানে লিভ করতে চাই, আমি জেনে রাখছি কি করতে হবে।
ওটা জাস্ট ওই পেজটা ক্রস করে দিলেই হবে, আর কিছু না।
মানে এই মেইন পেজটা?
হ্যাঁ, যেটা দিয়ে আপনি মানে যে মিটের যে পেজটা খোলা আছে ওটা ক্রস করে দিলেই হবে, মানে তাহলেই আপনি লগ আউট হয়ে যাবেন।
ওকে, থ্যাংক ইউ।
ভালো আছেন তো ম্যাম?
ভালো আছি, তুমি কেমন আছো?
হ্যাঁ ম্যাম, ভালো আছি।
সব বাড়িতে তো?
হ্যাঁ, ঠিক আছে, সবাই বাড়িতে।
আর তো উপায় নেই বাড়িতে থাকা ছাড়া। এখনো দেরি আছে, only 4:12।
ইয়েস ম্যাম, এখনো দেরি আছে 15 মিনিট মতো।
হ্যাঁ, ডিপার্টমেন্টের টিচাররা আর কেউ এসেছে?
আজকে তো এখনো পূর্বা ম্যাডাম এসেছেন, অন্নলক্ষ্মী ম্যাডাম এসেছেন।
অন্নলক্ষ্মী আর পূবালি তো আছে, আর কেউ আসার কথা?
এখনো তো জয়েন করেননি, মানে দেরি আছে, হয়তো করবেন পরে।
হ্যাঁ, এই তো।
রূপালী দি স্পিকার এসে গেলে আমাকে বলো কিন্তু।
পূর্বাদি, একবার শুরু হওয়ার আগে সবাইকে বলে দাও মিউট করতে আর ক্যামেরাটা অফ করতে, আর প্রেজেন্ট বাটনটা না টিপতে, ঠিক আছে?
হ্যাঁ, বলে দেবো বলে দেবো বলে দেবো। Everybody present here is hereby requested to keep yourselves on the mute mode.
Purba, does that mean you have to turn off the microphone?
Yes, Shormishtadi.
So I just press the turn off microphone button.
Yeah. Debanjana?
Yes, ma'am.
তুমি আজকে বলবে তো?
হ্যাঁ হ্যাঁ।
ওকে।
Purva, our first speaker, Dr. Gerard Pujadas, have already joined.
Okay, so we may start now then. Very good evening, everybody. This is the day 4 of our webinar series, international webinar series. And today also, like all the other days, it has been a very enriching experience because we have been listening to diverse kinds of fields of people, our revered speakers who have been enriching us. And today also we have 3 stalwarts in their own fields. So we are extremely proud, happy, and we earnestly welcome all of them in our webinar. So just a small request to all the participants for the smooth selling of the entire thing. Please cooperate and keep yourselves on the mute mode and don't press the present button. Thank you all so much. Now I would request our scholar Devanjana Sen to take over and introduce our revered speaker to the audience. Devanjana.
Thank you, ma'am. Thank you very much. Greetings and a very warm welcome to all of you on the 4th day of the International Webinar Series organized by the Department of Home Science, University of Calcutta on the occasion of National Nutrition Month 2020. Without further ado, we move on to today's main segment. Today we have 3 eminent speakers from different corners of the world. The first lecture will be delivered by Dr. Gerard Pujadas. Dr. Gerard Pujadas presently leads the research group on chemoinformatics and nutrition at Biochemistry and Biotechnology Department, Universitat Rovira i Virgili, Spain. He joined URB in 2002 as titular de Universidad on the biochemistry and molecular biology knowledge field. Then he integrated at the Nutrigenomics Research Group, where he was on charge of integrating drug discovery tools to study the effect of phytochemicals consumption on health. Since then, his main contributions to science has been the development of several virtual screening workflows for predicting molecules that act as anti-inflammatories or anti-diabetics, tools for validating virtual screening workflows, and tools for validating the coordinates of drug target complexes. Moreover, he has also contracts with the cosmetic industry to find natural compounds that can be incorporated in cosmetic products. As a result of this collaboration, 2 products with bioactive compounds discovered by them, namely Aqua Extreme and Melavoid, are currently on many products at the market. It's a king-sized excitement to hear Dr. Pujadas on the topic entitled Chemoinformatics for Functional Food, Molecular Cosmetics and Nutraceutics Applications. Audience, you please put yourselves on mute mode while the lecture is going on, and those who have questions, please type in the chat box. Welcome, sir. The platform is eagerly waiting for you.
Sir, please again present yourself. Someone has presented and your presentation has gone off. Please kindly present yourself.
Sir, you are not audible. Sir?
Sir, unmute yourself. Sir, please unmute yourself. Your screen.
One moment, please.
Sir, your screen is visible and we can hear you also. You may start.
Okay, one moment, please.
No, Purva, please let him again present it, because many of us will not be able to pin it.
Validi, the screen is already present. You just click on that particular screen.
One moment, please. Okay, thanks for your introduction, and sorry for the problems with sharing my presentation. Can you listen me now?
Yes, sir. You are audible now.
Yes, sir.
Okay, okay. I will talk about our experience as a research group by using chemoinformatics for functional food, molecular cosmetics, and nutraceutical applications. First of all, I will introduce a little of my institution. I belong to the Rovira i Virgili University. This is a university that is located in Tarragona. Tarragona is around 10 kilometers on the south of Barcelona. It's a relatively young university. In fact, it was created around 30 years, but it has, we think, a high quality, and here you can have some of the positions of the university in some of the more reputed rankings. We are very proud that we are among the first 100 universities in the world under the age of 50. Okay, relative to my group, we're a small group in the Rovira i Virgili University. We have four full professors in the research group, and some PhD students and graduate students that are making the graduate research work in our group. Here we have the link to the website of our research group, where you can find more information about all our research activities. Well, the first thing that you see here is the talk organization. I will start by introducing you chemoinformatics, because this word is a word that is not so popular than bioinformatics. What is the difference between bioinformatics and chemoinformatics? I think that the best way to understand the difference is to see which are the interests of both disciplines. In the case of bioinformatics, the idea is basically to make the analysis of protein or nucleic acid sequences or structures, or also to all the processing of omics results. Then these are the main topics of what we can call as bioinformatics. In the case of chemoinformatics, you have here some topics that are related with this area of research, but I think that basically the most important topic here is bioactivity prediction. The idea is that chemoinformatics is a discipline whose aim is to predict the bioactivity of small molecules. Then this can be done by several techniques like protein ligand docking, QSAR, drug design, etc. But basically, the main, we can say that the main topic is bioactivity prediction. Then we will, I will show now some of our activities in the bioactivity prediction of small ligands that can be of interest either for nutrition interest, basically for functional food design, or for cosmetic applications, but also for drugs, drug design. Well, which is the main difference between applying a virtual screening in the pharma industry versus the functional food industry or the cosmetic industry? Basically, the main difference is the type of molecules where we are looking for active compounds. In the case of the pharma industry doesn't mind if the compounds are only naturals or are synthetic molecules. In the case, this would be similar in the case of the cosmetic industry. Sometimes cosmetic industry only wants to find bioactive molecules and doesn't mind if their origin is natural or is not natural. But sometimes they want to look only for natural molecules for marketing reasons, and this can be also made. In the case of functional food, the only kind of molecules that we can search for bioactive molecules are small natural molecules. That means natural molecules that has been isolated, for instance, from plants, from marine organisms, for animals also, but basically for plants, also from insects, from bacteria. And this will be the main difference. In functional food, we can only add natural molecules as a bioactive molecules, and in pharma or cosmetic industry, they can use both kind of molecules. The difference between a virtual screening in the pharma industry and the functional food industry is the database of molecules that we use to look for the bioactive compounds. Well, we have been talking about virtual screening, and I will describe now what is a virtual screening, and which is also the main features of a virtual screening. Well, a virtual screening consists in finding bioactive molecules in a large database of molecules. Sometimes this is compared with finding a needle in a high-stake scenario. But I have to say that it's more difficult to find a needle in a high-stake scenario than find a bioactive compound in a database of molecules. Basically, the idea that make this virtual screening more easy is that in a virtual screening, you are using a kind of search that is guided by information. Then you use information, we will see which kind of information, but you use information that guide you during the search. In the case of finding a needle in a high stack, all the direction of the search are the same. Then you have no way to have information about where the needle is in this place. Okay. Well, what do you need to succeed in a virtual screening? The first is that you have to define which is the target that you want to work. The target usually is a protein, and you want to find small molecules that bind, usually with high affinity, to this target, and, for instance, block the action of this target, or or increase the action of this target. In other words, you want to modify the bioactivity of this target by binding to it a small molecule that will modify the function of this target. The first problem then is to select the target, which is the appropriate target for a virtual screening. It depends on the type of project. For instance, if you are working in the pharma industry, all the therapeutic targets, all the proteins that have a relevant role in the disease are potential targets. In the case of natural products, it's different. In natural products, usually it's quite difficult to have our 100% purity of the natural compound. Usually, you work with extracts that are rich in a specific natural compound, but you have also other molecules on this extract. And then, usually also a good difference with an important difference with drugs is that the concentration of the bioactive molecule in the natural extract usually is not so high as is a drug in a pill. No? Then, in the case that you are trying to use bioactive or making a virtual screen for natural compounds, you have to select a key target involved in an early metabolic stage of the disease development. Because usually in disease, you have a kind of cascade. Then if you block the first part, or initially, this will be a strong effect than going to endpoints. Then it's important to select the target, especially if you are working with natural compounds. It has to be a very important target for the disease development, and it is not so important in the case that you are working with drugs, with synthetic drugs, because you can make pills with high concentrations, not toxic. They have to be not toxic, these concentrations, but you have the power to have high concentrations of these drugs in a pill. Well, then the first you have to select the target. This is important, and then you have you need to have information for that target. Usually, it's important if you have the structure, the 3D structure of that target. This means that you know the position of all the atoms of the target in the space. And if this is not the case, if you have not the 3D structure of your protein, it's also good if you have the sequence, knowledge of the sequence of your protein target, because this will allow perhaps to build a model of the structure. If you don't have the structure, but you know the sequence, perhaps you will have the possibility to make a model of how could be the structure of this protein, knowing only the sequence. You also need to perform a virtual screen, bioactivity data on drugs that act on that target. These are two databases of bioactivity compounds. And the idea is that if you know drugs that act on your target, you can use the information about how these drugs are, how these drugs bind to the target, etc., to guide your cells. We will see this after. Here you have different levels of complexity in a virtual screening. You imagine you have selected your target, and here you have in columns information. You have here the PDB, that means that you have or not the structure. You have here the information about if you have or not the sequence of the target, and here you have the information about if you know drugs that act on your target. And in the different rows, you have different cases going from the ideal situation to the challenging situation. Then the ideal situation is that you have, in the protein, in the PDB, you have the structure, the 3D structure of a complex between your target and the drug. This is important because if you have this information, you can use, for instance, the interactions that the drug make with the target that are easily visible here to guide, to look for small molecules that make or can make potentially the same kind of interaction. Then it's important to know the complex between your target and a drug that have the same bioactivity that you are looking for your molecules. And you have also know the other drugs, not necessarily this one, but more drugs that have activity also in the same target. This will be the perfect situation and the easy situation to work. The next situation that is not so ideal than this is this second situation. In this case, you have the 3D structure of your target, but is in the free form. That means that you have no drug bound to the structure of your target, and then, for instance, in difference with this situation, you don't know what is the binding site of the drugs. Here you could see where it was, but here it's not possible to see because you have no drugs forming a complex with your protein, and you have the sequence, and you have this will be the second situation. This is more challenging than the first one because at first you have to know which is the binding site, and you have to predict which are the interactions between the target and the drug, and this is more challenging. Even more challenging is this situation where you have no information in the PDB about the structure of your target, but if you have the sequence of your protein, this protein and this sequence is similar to a protein that is in the PDB. There is a process that is a modeling process that is called an homology modeling that can use the protein that is in the PDB that is similar to your target to model, to make a model of your protein. This is more difficult because you build a model of your protein target, but this can have mistakes, and then it can introduce uncertainties in your result. And the most dissimilar situation is when you have no information about your protein target, you have no similar sequence at the PDB, then sorry, I am listening some sound in the headphones. Please, can you
Sorry, sir.
mute, please?
Yes, yes.
Thanks. Yes, this is the more challenging situation. You have no protein structure in the PDB for your target. There is no way to build an homology model. There is no way to make a homology modeling structure of your protein because although you have the sequence, there is no another protein similar in the PDB. Then it's not possible, and then you have only information on drugs. This is perhaps the most favorable situation. Okay, Then, if you are working in this situation, your results, your virtual screen results, are even more reliable than if you work in that situation. Well, what is the goal, the main goal of a virtual screening? Well, the main goal is that you start with a database of molecules, and then you apply different filters. You have here a first filter, you have here a second filter, and finally, you have some molecules that have the predicted bioactivity. During this process, you can see that you have here a funnel structure, a triangular structure for the typical virtual screening representation. And this means that when you are going on the virtual screening, you lose molecules, because when a molecule is not does not accomplish a filter, this molecule is rejected, and then in each filter you remove a part of the molecules that are candidates to be active. Then final, you have a predicted active that have succeed in the different filters that you have put in your virtual screen. You have here this in a sentence that is perhaps more clear. Well, now we will talk about these filters, the kind of filters that are going to be in these different steps. I have to mention before that here, as I told, which is the initial molecular database is important, because if you are working in the for instance in the functional food industry, then you have to be sure that all the molecules you have here are natural molecules. If you are in a drug industry, pharma industry, then this can be natural or synthetic. It doesn't mind in this aspect. Okay, we will now take a look to the main features of the different filters that we can use in a virtual screen. The first filter is the filter that is called the ADMET prediction. ADMET prediction is an acronym that is built with absorption, distribution, metabolism, excretion, and toxicity. The idea is that you have to use only in your drug discovery pipeline those molecules, those small molecules that have proper absorption, distribution, metabolism, excretion, and toxicity properties. Then all the rest have to be removed from the sample. Therefore, this is a kind of filter that is quite fast and can process millions of molecules in minutes, and then is usually the first kind of filter that is applied in any drug discovery process. The second kind of filter is a structure-based pharmacophore model. To have this kind of filter, you need to be in this scenario. You have to know the complex between your target and a drug. This will be ideal, because here you can look which are the main intermolecular interactions between the target and the drug. If you have not this complex and you have only the apoforms, you can use protein ligand docking. We will talk later about protein ligand docking to find the structure, to predict the structure of the possible complex. Even if you don't have the structure of your target, but you can make a model of a 3D model of his structure by the Homology Modelling. You can then use docking to predict which will be the complex of the target with a drug, and therefore in all these three scenarios, these three first scenarios, you can use this structure-based pharmacophore. Well, the idea is you have here a target, you have here a bioactive molecule, and you can see some arrows that show intermolecular interactions. For instance, in that case, this arrow indicates a hydrogen bond between this part of the ligand and this residue of the protein target. You have here more hydrogen bonds, then, and here you have other hydrogen bonds. Then, if you have a drug that has bioactivity on this target, and this drug has this kind of intermolecular interactions with the target, the idea is that if you find a molecule that is able to perform equivalent intermolecular interactions with the target, this molecule can be also active. Then this information is used to build a pharmacophore. A pharmacophore, you can see here the pharmacophore, has the information about how specific characteristics of the intermolecular interactions have to be in the 3D space for a ligand to be able to bind to the protein target. For instance, if here is not easy to see, but if you have here a hydrogen bond donor, this will, if a ligand can put here a hydrogen bond donor like this active, then it's easy to see that this ligand can make this hydrogen bond donor. Then you build a kind of pharmacophore is a kind of 3D map of intermolecular interactions that make a bioactive ligand, and the more intermolecular interactions of these accomplish your molecules, you have the most possibilities of being active also with that target. Well, in virtual screening, another kind of methodology that is quite normally used is protein ligand docking. In our case, we don't use protein ligand docking as a filter because we are not very happy with that use of protein ligand docking, but we think that protein ligand docking is useful for predicting the coordinates, the putative coordinates for the protein ligand complexes from the individual coordinates of the target and the ligand. Here you have the target. Here you have the structure of a probable or a putative ligand of the target, a putative reactive molecule that bind to the target. And the idea of docking is that after applying a protein ligand docking, you will have the predicted 3D structure of the complex between the ligand and the target. Usually, in the protein ligand docking process, the target is fixed. The coordinates the protein is rigid. Then the coordinates of the different residues cannot be changed. And in the case of the molecules, if you have in the case of the ligands, if you have single bond, then single bonds are allowed to rotate. Then the conformation of the ligand here is not the same that the starting conformation of the ligand, but the conformation of the protein on target is the same here and here. Well, it's important, as I said you before, there are many people that use protein ligand docking as a filter, but we think that we are not happy with we are not very happy with this idea, and why I will explain now why. In here you have the typical component of components of any protein ligand docking programs. There are plenty of protein ligand docking programs, but they are built in this schema, all of them. First, you have a search algorithm, and then you have a scoring function. The idea of the search algorithm is that this algorithm looks for the different conformations that can have the ligand at the ligand protein ligand binding site. And this is a part. This can be done in different ways. For instance, I will explain now how this part is performed by the HITS program. Here, for instance, you have a ligand, and then you divide the ligand into rigid parts. Then you dock the rigid parts, and finally you try to connect the different rigid parts with the flexible linkers, and you then find which are the probably, here there is only one possible situation, but you can have different possible situations of the docking results. Well, this kind of this step of the docking protein ligand docking software, the search algorithm, is quite efficient, and really it works very well. Then we can tell that all or nearly all the protein ligand docking software are able to reproduce the experimental conformation of the ligand in the protein ligand complex. The experimental conformation of the ligand is what we call the ligand pose. Okay, then the search algorithms work quite well, but the problem is in the second part, scoring function. The scoring function, the idea of the scoring function is to make a rank of the solutions that have been found by the search algorithms. And here, if you have the same solutions but different scoring functions, you will have a different ranking. And this is a problem because if you only rely on the first solution of the rank, depending on the scoring function, you will have different solutions in the first position. Then using protein ligand docking is, for us, is quite interesting for finding which are the possible conformations of the ligands in the binding site, but we don't rely on the scoring function results. And sometimes it's quite easy to find people that make a study and use only protein ligand dockings to rank molecules, and then they establish a threshold, and the results that are above these thresholds are considered the solutions. And this is not true, because depending on the scaling function, you will have completely different results. But protein ligand docking is useful for us for finding which are the probably orientation of the ligands in the binding site. Another kind of filter is shape similarity. You have here two molecules. This is a known active. You have here the two-dimensional structure, the chemical structure of that active, and here you have the two-dimensional structure of a molecule that is predicted as active. As you can see, the chemical structure is quite different, but the shape is not so different, and therefore, in the case of the protein target, although the ligand is different, they can see nearly the same. If instead of comparing the shape, we use the same molecules, but we compare the electrostatic surface. You have here in red, you will have here the negative surfaces, and in blue the positive surfaces. The molecules are the same, the conformations are the same than here, but you can see that even if the structures are completely different, where they put the electrostatic positive charge and the negative charge and the positive charge relative to the target is quite similar, then it is quite easy to understand that from a target point of view, this molecule, if this molecule is active, this is possibly also active because it can make a similar intermolecular interaction. Well, the idea then is that you use different filters in a virtual screen. These filters are knowledge-based. You use information on drugs that have the same bioactivity on the target to guide your search. And this was I told before that finding activities by virtual screening is a knowledge-based search. It's guided by knowledge search, knowledge information. Well, virtual screening validation is very important because sometimes there are some articles that report to you the information from different from a docking, for instance, or from a virtual screen, but if they don't go to the lab and prove that in vitro, for instance, that the predictions they have made, then it's quite difficult to think that the predictions are correct or not. Then making a validation of the virtual screening is always necessary to at least to have an idea of if the virtual screening is able to find really true positive and that the molecules you have as a hit at the end of the virtual screening are not false positive. One way to do that is quite simple, is to use the same virtual screening with a set of molecules that where you know the bioactivity. In the case of actives, these are drugs that are active against the target of interest. And in the case of decoys, these are molecules that are not active against the same target. Usually, decoys are calculated. It's quite difficult to find information about inactive molecules in the literature and databases. And usually, the idea is to use molecules that are similar to the active in the molecular weight similar to the active, but that are arbitrarily chosen. Okay. The idea is that you start with a large number of decoys, and in comparison with the number of actives, you go through the different steps of the virtual screen, and finally, if your virtual screen is working, you have to see that the concentration, the proportion of the active at the end of the virtual screening has to be significantly higher than at the beginning. Here you had only 62 active and more than 10,000 decoys molecules, and here you have loose actives. You have only active. You have false negative that have been removed in the virtual screen, but you can see that the virtual screening is more efficient in removing from the sample non-active molecules than active molecules. That at the end you have a concentration of active molecule that is higher than at the beginning. This is very important. It's very important that when you publish results about a virtual screen, you had a validation, at least a theoretical validation that is the kind of validation that I am showing here for your virtual screening workflow. Now I will see an example of application of virtual screening. In that case, it was a work that we made some time ago, and the idea was to find inhibitors of this target. This target is AK2. Is a target that is implicated in a lot of processes that you can see here, and the idea was to find inhibitors of that kinase. This was published. This was made in collaboration with a team in the Swiss Institute of Bioinformatics in Lausanne, and published it in PLOS ONE. The idea was to establish a virtual screening, and first here you have the validation. We make, in that case, we make different filters. You can see here the different filters. You can see here how many actives survived each filter, how many echoes survived each filter, and before we have here the information that at least in theory the virtual screening was working properly, because remove a large proportion of the decoys and keeps a large proportion of the actives. Well, we finally obtained from these 14 hits, we bought 5 of them, and we find that 3 of these 5 were active. We go to the lab and make this test. Then we had nearly 60% of success. This was not so well, and the idea was to apply this virtual screening to find. I have not said, but this is this kind of this target AKK2 is important for inflammation, and you have that chronic inflammation is in the background of a lot of process. For example, diabetes is a metabolic syndrome. That is, diabetics is a part of metabolic syndrome, and then finding natural products that can inhibit this kinase are important. For instance, for the design of functional food that is directed to people that are diabetic or have metabolic syndrome. Then the idea was to use this virtual screening workflow to find AKK2 inhibitors in non-toxic mushroom without gastronomic use. There are here in Catalonia, there are forests with a lot of tradition of the people go to take mushrooms to eat, but there are a lot that are not toxic but are not used, and the idea was to take profit of this biomass and to use them to find a profit. Well, we built a database of the different kind of mushrooms with these characteristics we have. We built a database. We find we find 62 molecules that are in this species of mushrooms. We apply the virtual screening, and finally we find some mushrooms that can have some molecules that can inhibit this target. Here we have evaluation of the inhibition of the potential inhibition of the structure of different of these mushrooms. We have here without inhibitor, and we can see that when we use this is a commercial inhibitor of the EKK2, and with a struct of this mushroom we obtain similar inhibitions. Then structures of these mushrooms can be interesting for including them in functional foods for this target of population that is affected by chronic inflammation-based diseases. Well, we make a publication of this in agriculture and food chemistry. And finally, to finish my talk, I will talk now a little bit about our current areas of interest. We're working with the cosmetic industry, as in the as it was mentioned in the presentation. We have been working with cosmetic industry to find bioactive ingredients. In that case, Metabolite, that was mentioned, was a natural compound, natural-based product that we find the bioactive molecules by virtual screening. In that case, it was an agonist of piper gamma, and this was a prize that was obtained by this product based on this natural product in this cosmetic event. More recently, we have started to apply our knowledge to fight against COVID-19, and we made this publication that was published in May, at the end of May, in International Journal of Molecular Science, and where we use a virtual screening workflow to make a drug reposition. That means to find available drugs, approved drugs, then drugs that are in the market, to block the action of this main protease of the SARS-CoV-2 virus. Well, the idea is that here you can see the abstract of the paper, only for guiding you about the process. As I mentioned before, this target is very important. The main protease of the virus is a key target for antiviral drugs, because this is a target, is a protease that coats the polyprotein that is synthesized by the virus, and then if this protease is blocked, the virus cannot progress and cannot infect the human cell. Then it's a quite important target for this disease, and in fact, in nearly 6 months, there are in the PDV around 200 structures of this target, and is the protein of the virus that is of this virus that has more structures in that database. Well, in that case, can you mute, please? Okay, thanks. In that case, there was information when we started the project. There was information on the structure of this protease, but there was not information on drugs that can block this target. Then the idea was to use 2 libraries of approved drugs. In that case, 2 libraries that were complementary, that has not exactly the same information, because the idea was to make a reposition of drugs. That means to use a drug that, for instance, or to find a drug that, for instance, is used for headache treatment, to see if this drug can block this protease. And this is important because, as you know, if a drug is approved for one use, it's more easy to find legally. It's more easy to find or to use for novel applications that a completely new drug that has to be studied with the different phase 1, phase 2, phase 3 until being approved. Then the idea was to find some kind of drugs in the approved set that was able to be used against this protease. Well, as I said before, there was no information about other drugs that can block this protease. Then the idea is to make a docking with the protein target and see which were the results of that docking. As I said to you before, we don't like very much docking to make decisions, because docking programs work very well from finding the probably conformations of the ligands, but depending on the scoring function, if you only rely on the first on the top result, you will have different solutions. Then the idea was here to use 3 different docking programs, in that case Glide, Fred, and Autodoc Bina. The 3 programs have the same goal, but the process, the algorithm is completely different for the 3 programs. And the idea is to keep around 10, the first 10 results for each ligand for Glide, the first 10 results for each ligand for Fred, the first 10 results for each ligand for Autodoc ligand, and then compare the 10 results from Glide, the 10 results from each result from Glide with the 10 results from Fred and the 10 results from Bina. The idea is that if the 3 programs arrive to the same solution, irrespective of that, this solution has been ranked by Glide the first, but Fred first ranked it as the 10th, and Autodoc Bina first ranked it as the 7th. If the 3 programs arrive to the same solutions, considering that the scoring algorithm can give you different results, but that the programs are especially well designed to find the probability process, experimental conformations of the ligands, then you have found the solutions. Then we use this procedures with virtual schemes with these 2 databases, and finally we predicted 7 inhibitors of this protease. You have here the list of the 7, and this was a prediction, and finally we have with the collaboration of the COVID Moonshot initiative, 3 of these 7 molecules were selected for in vitro testing. Here there are only 2, but sarafloxacin that is in the list was selected for a second round of in vitro testing. And finally, the 3 molecules show experimentally in vitro that they are able to inhibit this protease, the main protease of the SARS-CoV-2. They are not very potent. In the case of sarafloxacin, is 20% of inhibition at 50 micromolar. Sarafloxacin is more potent than carprofen and celecoxib, but they can be starting points for treatment, and also for building drugs, analogs of these compounds that can be more potent. We are quite happy because one of these drugs, celecoxib, has given promising results in vivo. Here there is a preprint. That means that it has not been peer-reviewed. Then we have to take with care these results. But this was a study that was published more or less simultaneously with our computational work, where they use celecoxib. Celebrex is the commercial name of celecoxib in a core of in a hospital in China, and they see excellent results. In fact, from 35 persons that was administered celecoxib, and that were all of them positive with of COVID-19, they recovered quite fast. And more recently, we have found also a preprint from the USA, where in a hospital, these authors use a combination, a combined therapy with celecoxib and famotidine to treatment of these COVID-19 patients with significant clinical answers. Also, our findings receive quite attention from the media. Here you have a screen capture of the new in the Reuters agency of India, I think, that they announced our findings. And well, I think we have here more details, if you want, of the experimental process we use it, of the virtual screening process we use it. And well, this is all my talk. And if you have, thanks for your attention. If you have any questions, I am here.
Thank you, sir. Thank you so much for this informative session. There are so many questions. With your permission, I would like to begin, sir.
Okay.
Yeah. The first question is, if the protein sequence has some missing or repeated sequence numbers, then what should we do?
Can you repeat the question? Because I haven't understood it.
Yes.
Please.
If the protein sequence has some missing or repeated sequence numbers, then what should we do? Hello?
It refers to the, yes, yeah, I am thinking, because I don't understand the question. I don't know it refers to the protein target if we don't only know the sequence. I will connect the a moment.
Okay.
One moment, please.
Yes, sir.
Devanjana, go to the next question.
Okay, ma'am. If the protein needs some cofactors to work with, then should we add these ions? Add those ions, what should be their charges?
Yes, of course. If the protein target needs a cofactor, you have to include this in the structure during the docking. Yes, and during the docking and in all the simulation, of course. Yeah.
Okay, sir. The next one is, could you please mention name of some databases where I can find bioactive compounds of several food?
Well, yes, there are some databases, and there is a database that is. Do you see now my screen, the screen of my computer?
Yes, sir.
Yeah, there is a database that is called Supernatural, where you. Okay, a moment. That this is a database of natural compounds, a public database of natural compounds. And then if you are interested in natural compounds, you can download the structure of these compounds from this database. There is, if you are interested in synthetic compounds, perhaps the more important is the zinc database. This is not zinc database. And this database is a database where of compounds. These are really yet to be used for virtual screening. And it contains, here you can see, it's a large quantity, 2,030 million of purchasable compounds. That means that if you use this database for making a virtual screening and you find interesting compounds, you can use these compounds you can buy these compounds and test in your lab if the bioactivity is really or is these compounds are true positive or not. We also use a library of a company that is Specs. This is as a company specs. Specs.
Pardon, sir, the screen is not visible. The software you named just.
Oh, sorry. I am sorry.
No,
Yes. Well, this database is from a company that is called specs. And the advantage of using these compounds, the library of this company to, for instance, to test your virtual screening is that the compounds here are really cheap. You can buy 5 milligrams of compound around with a price that is around $20. Then it's quite cheap because with $400 you can test 20 compounds that if you selected well these compounds, it's enough to be sure how your virtual experimentally how your virtual screening is going. Is it really working well or not?
okay. Sir, the next question is there any software which will help to find out whether the ligand is inhibiting or activating those targets?
Yes, you have. There are a lot of resources on the web. Basically, it's more easy to find if a ligand blocks, if a ligand inhibits a target, that if a ligand activates a target. Basically, if you want to inhibit a target, you have to block the active site. Whereas in the case that if you want to activate that target, usually you have to find an allosteric site, and this is quite it's more difficult because then you produce changes in the structure of the target, and one of the things that are quite difficult to model is how a target is answering to the binding of a ligand. There are techniques like molecular dynamics that can give you some kind of information, but are simulations. Then it's more easy. The idea is that it's more easy to find inhibitors than activators. Then, if you want to find target resources to use, for instance, you have the Swiss doc. That is this is from the Swiss Bioinformatics Institute. And here you can make online without installing any software in your computer. You can make a docking, a limited docking, because it is not possible to dock automatically several ligands in the same target. You have to make one by one. But if you have to only try to find if a ligand can bind or not to a target, you can start here.
The next question is, nowadays during this COVID-19 pandemic, we are hearing a lot about immunity boosting foods. In this present scenario, what are the avenues that can be explored in the field of nutrition, immunity and informatics, and how can they be interlinked?
Can you repeat the question, please?
Yes, sir. During this COVID-19 pandemic, we are hearing a lot about immunity boosting foods. In this present scenario, what are the avenues that can be explored in the field of nutrition, immunity and informatics, and how can they be interlinked?
Oh, well, this is difficult because making docking between protein docking is not my area of expertise. Then it's my area of expertise is more related with protein ligand docking or protein ligand small molecule interaction.
Mhm. Okay, sir. The next question is, how are the metabolite profiling target studies carried out?
I suppose that this question refers to how we select the target. Uh, well, as I mentioned in the presentation, it depends on your role. If you are trying to use data, if you are trying to use natural compounds, you have to be you have to find a key target in the metabolism of your disease, because you will have a slow concentration of the bioactive compound in your extract. Then if you use synthetic compounds, um, you can use nearly all target endpoints also of the metabolisms to make the virtual screening. But I think that using key points, key targets, will be also more effective, even if you use synthetic compounds.
Thank you, sir. The next question is, sir, can you please highlight on the multivariate data analysis techniques of herbal extracts? Hello. Hello. Hello, sir. Hello. Hello.
Yes,
Hello.
Devanjana.
Yes, ma'am. I think sir has left the meeting. Why? Due to some connection network problem.
There must be some network problem. Our Pubalidi is here.
Madam.
Yes, I am here. Yes, I am here.
So, can you contact sir? What happened? Abruptly, the meeting ended.
Oh, I have no phone number. I have no contact number, so I have to mail. Uh-huh.
Is our next speaker with
Can
us?
we ask? No, no, I'm calling Orijita.
Hello, audience. Please bear with us.
It seems that there is a technical snag, so that our first speaker, while answering the questions, he got disconnected, and our head is trying to contact the next speaker. So we have to wait in the meantime. So our next speaker, Orijita Di, seems to be with us. So, dear audience, extremely sorry for the abrupt ending of the first lecture. So, our next speaker is Professor Orijita Dotto from Department of Economics from our university. Um, Without wasting much of time because of the technical snag, and you all are maybe now impatient by now. So I would request Debanjana, our scholar, to please introduce our revered speaker to the audience and welcome her.
Thank you, ma'am. Our next lecture will be delivered by Professor Arijita Datta. Professor Arijita Datta is currently working as a professor and head of the Department of Economics in the University of Calcutta, India. Her research interest is health economics, quantitative development economics, and econometrics. Professor Datta has a number of publications in national and international journals to her credit. She has been closely associated with health policy making of the state of West Bengal and has published a number of policy documents on healthcare in West Bengal. She has taught and has been a visiting researcher in a number of European universities. Currently, she is acting as a successful coordinator of UGC DSA program and the co-editor of in-house journal Arthaniti. Just a few years ago, Professor Datta had shown that the access to integrated child development scheme faced certain serious socio-economic barriers in different regions in India, thus limiting the intervention net of the central government. Her study succinctly pointed out certain policy implications for different states in the country depending on their regional socio-economic milieu. It's our immense delight to hear Professor Datta on the topic entitled Economics of Nutrition, Some Issues and Applications. Audience, you are being requested to put yourselves on mute mode while the lecture is going on, and please type in your questions in the chat box. I would request now Professor Orijita Datta to take over. Ma'am, please.
Orijita Di, please unmute yourself. Orijita Di, please unmute yourself.
Yes.
Thank you. Welcome.
Thank you, Debanjana, for
Thank
this
you, ma'am.
very nice introduction. I also thank, at the onset, I also thank the head of the Department of Home Science Department and also the other faculty members, including Purba, for inviting me to present in this very prestigious international webinar. I'm happy to be a part of it because I'm actually a part of the CU family. So I would like to present directly going on, presenting. Can you see? Can you see the slides?
Yes, ma'am.
Yes, we can see the slides.
Okay. Thank you. So I start with, see, the issue of nutrition emerged in our curriculum since our school days. So we knew from the school textbooks that what to eat, what is balanced diet, and what should be the things that we will be eating for different diseases, etc., etc. Now, nutritionists, doctors, health professionals, they are the ones who were always involved in these things in terms of nutrition, prescribing something, telling us not to have these things, no junk food, etc. But what are the economists doing in nutrition? What do they have anything to add? That was the first question that I faced when I started working in different issues, on different issues related to nutrition. And I found that the role of economists have not always been very accepted or recognized in this area. Now, what economists can do is to find how nutrition can improve the productivity, and also look at evaluation of nutrition program to reduce the malnutrition. So with this introduction, I move on to what we mean by the basic theory. Don't get perturbed with these figures. I will, or all the maths. I will not go into any detailed or high maths. I'll just introduce what are our basic problem in economics. So the basic theory in economics is consumer utility maximization. So what we do, we maximize U, that is the utility function of the individual, xi, x1, x2 to xk. These are the amounts of the ith food. So if I assume that a person intakes k numbers of food, so I take x1, x2 and xk food, and from having consuming these each food, I derive some amount of utility. Now, what is my basic objective is to maximize that utility derived from x1, x2, and xk. But I have a constraint. And what is that constraint? That I cannot spend more than what I earn. So that income is given by y on the right hand side of the inequality. And on the left hand side, we have the total expenditure to be spent on buying x1 units of x1, x2 units of capital X second good, xk unit of the kth good. So this is P1 into x1 plus P2 into x2 plus pk into xk. This is the total expenditure. And that should be less than or equal to y. So basically, in terms of economics, this is the budget constraint. Because I always want to have the best foods that are available. I want to have, in my breakfast, I want to have kiwis. In the lunch, I want to have quinoas. And in dinner, maybe a roasted chicken. But as you can understand that not all people, particularly from the developing countries, but also from developed countries, they cannot afford to have these kinds of food in each meals. So there is a budget constraint. And also utility function depends upon in terms of nutrition, we need to specify something else as well. So what, apart from this, in nutrition economics, we need to specify few more constraints. And one of those constraints is regarding the time. So basically, I need some time for buying the food, cooking the food, having the food, and then leaving some time to assimilate the food in my body. So if I take that T1, T2, T3, T4, and etc., so the entire numbers of T's together should come as equal to 24 hours. So that is another new constraint that we should consider. Not only that, utility function should also depend upon the variable zi's. And this zi's which takes care of the assimilation capacity of the individual. You know, what we find in every day that even if I take best of the foods, best of the nutritious food, my health does not become that good as my neighbors. So it's basically my assimilative capacity of my body, assimilation capacity of my body, that makes the difference. And that is probably driven by some genetic variables. So considering all those things as Z1, my utility maximization, which is the standard economic maximization, is like this. From here, we move to maximization of utility, which now is not only a function of x1, x2, x3, but also z1 and t1 and t2. And the constraints is not only in terms of E1. E1 is actually the expenditure on X1, that is P1 plus X1. E2 is P2 into X2. So the first constraint remains as E1 plus E2 plus E3 is, there's a typo, this should be less than equal to Y. And the last constraint would be T1 plus T2 plus Tn, should be equal to 24. So it is actually very interesting to find that how economics can take care of the nutrition issues, but with some modified modelings. So today what I am going to say is that there is a two-way relationship between economics and nutrition. The first one is the nutrition influences economic conditions via human capital. And what are the human capitals that are going to be changed is better education, better health, better productivity, and more income. So essentially, we need to say that nutrition, better nutrition, increases the better education, creates better health, and hence better productivity and better income. On the other hand, the other way relationship is also true when we find economic condition influences better nutrition via better intake of food, hygiene, and care. So on what we find that economic conditions and nutrition, they are related to each other in a two-way method. So first I talk about the nutrition affecting the income condition, economic conditions. Now, it was the economic historian Robert Fogel in 2004 who had argued that improved nutrition was a decisive factor for improved health and successful economic development in Europe and the United States during the 19th and 20th centuries. So, the economic flourish that currently we see in USA and in Europe in 19th and 20th centuries, one of the major determining factor was nutrition. The nutrition improvement, the reduction of malnourishment, etc. Better nutrition improves overall better health, better learning ability, and hence better productivity. What we eat determines what enters our bloodstream, and also our brain function is one of the most obvious exhibitors of your body's health. When it's healthy, you are focused. So that is how we look at it, that with nutrition, I am sure that I do not need any elaboration on this part, that how better nutrition can improve my better functioning of my health, of my body and my brain. Now, continuing on this, according to the flagship study released on the subject by ILO, that is International Labour Organization in 2005, we find that nutrition habits have a direct impact on our productivity. And WHO in its study actually points out that adequate nourishment can raise the national productivity level by 20%. So it's a huge number. Now, researchers told children to skip, this is a kind of an experiment that they had, this ILO study. They told children to skip their breakfast before coming to school. Half of the children were randomly selected and they were given to eat a nutritious breakfast while at school, and the rest were given nothing to eat. So what were the results? According to the study, the results were incredible. Those who had eaten breakfast had fewer behavioral problems and higher learning patterns than those who had not. When those who had not had breakfast were given a snack, their success improved as well. So if the children receive nutritious breakfast or even at least a snack, their productivity, their learning capacity improves dramatically. Now, coming into, I want to here focus on micronutrients. Now, whenever we talk about nutrition, we all know that there are majorly two types of foods. One is the energy food, and the other is the micronutrients, the vitamins. And as a lack of micronutrients, a lot of diseases occur. In this figure, we are going to present three things for the across the country study, and that is for 4 years, right? Now, On the first panel A, we have per capita daily average energy availability. Panel B, we have micronutrient density index. And in panel C, we have prevalence of inadequate micronutrient intake index. So this is basically the gap. This is the micronutrient intake, and this is the daily average availability of energy foods. So it's basically, the study have looked at for the world and 7 regions. The summary of the results is something like this: the global trend of micronutrient availability. From 1961 to the 80s, the MDI declined in most regions, particularly in Latin America and in East and Southeast Asia. So this is the micronutrient density index, which you can find clearly that there was a drop in East Asia. There was a drop in Latin America as well. So the micronutrient intake definitely dropped during the first half of the study, that is 61 to 76 up to 80s. The MDI had risen in most of the regions since 1980s, but this reason appears to be tapering off in East Asia and Latin America. Again, going here. So after this, you find that there is a clear increase in the micronutrient density index. Similarly, for the high income countries and also for South Asia. But beyond the time after 2000, there is a kind of tapering off. The MDI declined dramatically from 1979 to 93 in sub-Saharan Africa. And this is very important, that why did it decline? Due to the increased availability of lower micronutrient dense grains like rice, maize and wheat and vegetable oils, and decreased proportional availability of pulses, dairy products, meats, nuts and seeds and fruits. So going back for sub-Saharan Africa, this is the red one. So you find that what has happened here, though the per capita availability of energy availability has increased substantially, the micronutrient densities has gone down. Why I am saying this is very important, because India, when we will be discussing, we will find that also faces a similar kind of a thing when after the globalization, and particularly initially with the start of the Green Revolution phase and after the globalization, there has been a decline in the products, in the agricultural products, which are more densely, which are more dense in micronutrients. And we also had less availability of pulses and other coarse cereals. So that might also affect the micronutrient availability among the Indians. Now, throughout most of this period, Southeast Asia had the lowest MDI for all the regions, largely because of high proportion of white rice in diet and low amount of animal source foods. But since 2000, it has been a similar MDI to that of sub-Saharan Africa. So if you look at the South Asian story, see, South Asia, apart from Southeast Asia, right? So this has been lying lowest among the regions. So given this condition of global trend, let's talk about the map. So you find that over the years, in terms of the micronutrient density index, see, from 1961, 86, 2011, India's position, actually, India's color has not improved much, right? And it has remained almost in the orange zones, and it has not improved much. Whereas many of the other neighboring countries have actually moved to lighter yellowish regions, which indicate that they are improving. For example, definite example is China. So there has been a significant improvement in this. Also, if you look at the Latin American countries, there has been a marked change in the micronutrient density. So what we move on to, that Levin in 1986 summarizes 8 experimental studies that analyze the relationship between blood iron levels and productivity, and concludes that the output elasticity of hemoglobin levels is as high as between 1 and 2. So that means that if the blood iron level increases, the productivity, the overall productivity would increase. Now, based on the same estimates, a recent study suggests in some South Asian countries, losses in GDP due to micronutrient malnutrition as high as 2 to 3% of their GDP. Now, the micronutrient elasticities on veggies, the sample mean in India appear to be lower in these studies. It's
Pardon,
not
ma'am.
as...
Can you please present your screen once again? Somebody else presented. That's why your screen got. Sorry, ma'am, interrupting.
But whoever is presenting, he or she will have to stop presenting.
Yes. George Puertos, please stop presenting. George Puertos, please stop presenting. Yes, ma'am, you can now present.
It's okay?
Yes, ma'am, yes, ma'am. Thank you, ma'am.
Okay. So, so the if the blood iron level increases, the overall productivity increases. Now, lifting current intake levels by 50% indicates that average total household productivity increases would be in the range of 5% to 17%. The results that demonstrate, this is for India, that policy interventions that aim at enhancing micronutrient intake are not merely ends in themselves. They can be regarded as investments in improved productivity and higher incomes. So what I'm seeing, that when the person is improving their diet in terms of iron rich diets, it's not just the food is being taken and it is just for the micronutrient intakes increased, but it's a kind of an investment for the future productivity and helps on higher household incomes. Now, there are 4 leading causes of death in United States, and they are heart disease, cancer, stroke, and diabetes. Medical studies point out that all these four main diseases are actually influenced by dietary choices. So increased rates of overweight and obesity in recent decades in the developed countries have been associated with each of these diseases. Now, this has happened at the time as rates of being overweight or obese among adults have increased from 50% of men and 40% of women in the early 1960s to nearly 75% of men and over 60% of women in the mid-late 2000s. So this is the story of United States, where over the last 40 years, there has been a substantial increase in the share of obese and overweight adults. And that is, studies reveal that that is particularly associated with very different kind of food intakes. Now, coming to the second link, that is from economy to food intake. So far, we have discussed about from food intake, nutrition to economy. Now, I'm looking at the economy to food intake. Now, the poverty amplifies the risks of and the risk from malnutrition. We all know that. Now, the people who are poor are more likely to be affected by different forms of malnutrition. Also, malnutrition increases healthcare costs, reduces productivity, and shows economic growth. So, therefore, there is a perpetuate cycle. It's a kind of vicious cycle from poverty to ill health, from ill health to from poverty to low food intake, to low food intake to ill health, and from ill health again to bad productivity and hence poor economy. So the income poverty can lead the households to food insecurity, inadequate care, unhealthy household environment, and lack of health services. And that is what we find, that people of low socioeconomic status are most vulnerable to food insecurity. You know, it's not just the income, but it's the socioeconomic gradient that makes the nutrition a very, very difficult thing. So households that cannot attain nutritious foods due to income poverty are most associated with inadequate diet and disease that leads to malnutrition. But higher income people might have malnutrition also because of wrong choice of food. And when we talk about this, we must consider that malnutrition is not just undernutrition. It can be in the form of obese or over intake of food. And so, hence, in terms of certain indicators, the higher income group is not always associated with better nutrition and better health. There may be a lot of people who are taking wrong choice of food. I guess that in this audience, there are a lot of young generation people. And also, when I discuss this in my class, I also talk to my students. In fact, in 1 year, I had done a survey of what is the tiffin that they carry with their when they come to the university. So it revealed actually that they have a choice for better tasty foods rather than better nutritious food. Now, it's not a problem. That's again a rational choice. Being a student of economics, I think that's also a rational choice. But when this is done by somebody who does not understand that, then it's a rational choice. But for a student who is completely aware of these things and then again also indulging themselves for this kind of fast food intake, this is actually not very rational. So the young people should also remember that taking these very highly oily foods and these tasty foods may not give them the nutrition, and hence that's a kind of a disinvestment on their health and on their future income. Now, the link between economy and malnutrition is often blurred, as I said. There is a very important study by Ravi and Radhakrishna in 2004, which came out in EPW, which analyzes the trends in malnutrition over the past 2 decades and shows that the improvements in nutrition status have not kept pace with the reduction in poverty, and current level of malnutrition is unacceptably high. Now here, to this audience, I'm sure that I need not discuss about the anthropometric measures of malnutrition, and that is why I have not discussed here. Just as a passing reference, I want to mention that there are wasting and there are stunting and overall malnutrition. So it was found from the Ravi and Radhakrishna's paper that the current level of stunting children in India is unacceptably high. About half of the preschool children are malnourished and are exposed to risk of functional impairments. And malnutrition levels are uneven across states as well. So some middle-income states such as Kerala and Tamil Nadu have comparatively better nutritional achievements than the relatively higher income states like Maharashtra and Gujarat. they have their malnutrition incidence is not only higher than the national average, but also it's higher than most of the states. So what we just think that when it comes to the question of malnourishment to us, we think it's just in that map. It's just the, excuse me, there is just Bihar, UP, and Madhya Pradesh. No, you are wrong. The highest incidence of malnourishment is actually in is found in relatively more high income states like Maharashtra and Gujarat. Northeastern states are comparatively better performing states, and some of them have even outperformed Kerala. So given this study, what we find that the world policy metrics to curb malnutrition among the children has overwhelmingly attempted to create enhanced access to supplementary nutrition. As we had just discussed, that in the low-income households, since the availability of food is less and the availability of high nutritious food is less, so there the policy metrics have been to provide a supplementary nutrition, particularly to the children, energy-rich food grains, when occupied, coupled with awareness generation programs. However, social scientists have identified that apart from food energy intake, certain non-food attributes, including access to safe drinking water, sanitation, healthcare, and environmental hygiene, are more important in malnutrition. And therefore, just the supplementary nutritional program, or SNP, have in most of the cases failed to garner improvement in malnutrition status among the children unequivocally. So here I come to the almost the third part of my presentation, where I talk about the policy. An integrated child development scheme, or the ICDS, is one of the oldest central sponsored scheme. It started in 1975, and from 2000 it became universal for all the districts in India. Now, ICDS consists of 4 different components. And what are they? Early childhood care, education and development, care and nutritional counseling, health services, community mobilization awareness, advocacy and information, education and communication. So apart from the main methods with which the ICDS work is, number one, it is providing supplementary nutritional food to the children and to the lactating and pregnant mothers. Then the preschool education for the children, some health checkups for the children and the mothers, and the most important is the advocacy, information and mobilization awareness. Now, studies from the 1990s generally found program placement that was skewed towards well-off districts and no effects on anthropometrics outcomes. Now, after that, when it was, in 2000, it was made a kind of an universal program. In spite of significant increase in access to food grains and initiation of S&P program, India has continued to bear a very high burden of child malnutrition till date. However, most assessments of ICDS has so far located limited evidence, as I just pointed out, and among them, very important ones are by Devlalikar, 2005, and by Lakshan Gupta and Gangloti, which is 2005. And there was another paper by Jain, Singh and Pathak, which concluded that only the girls of 0 to 2 years receiving supplementary nutrition regularly tended to at least 1 centimeter taller than the similar girls who did not receive it. And there was no that robust impact on the boys. Now, between 2006 and 2016, the coverage improved significantly, but the services tilted towards more wealthier households. So given this backdrop, I would talk about a little about one of my papers with my scholar, Sritika Ghosh, in 2006, which came out in Mother's Nutrition Journal, MCN, which has a very high impact factor. And it's based on a primary survey on 390 households and 65 Anganwadi centers conducted in 2 districts in West Bengal. And the districts that we considered were Howrah and Uttar Dinajpur. We chose Howrah and Uttar Dinajpur based on an index that we created. And Howrah is a better for performing district, closer to West Bengal's capital, Calcutta. And Uttar Dinajpur is located in West Bengal, North Bengal. And most of the development indicators are very poor. And what we have done is the propensity score matching. I will not go into the details of the methodology, but it's a kind of an impact assessment methodology that we have used, where I have matched one person, one child who has received the SNP with another child who has not received the SNP, but with similar characteristics. So this is a method of impact assessment, and we have used propensity score matching. Now, before going into the direct results, I'd like to mention that any program has 3 dimensions. The one is the breadth, that is the who is covered, what is the share of the population who is covered. So that is the coverage. Now, the depth is which services are covered, what are the services that are provided, and the height is the cost, that is reduction in the costs. So if you look at the program as initial cube, the green cube as the initial condition, and the policy targets to reach this cube. So that means it will not be sufficient if only the breadth is increased, but it also needs the depth to be increased and height to be increased. So given this kind of the universal programs, what we do, I present here that the depth of the services. So it's not the question that who went to the Anganwadi centers and who did not, but once they reached the Anganwadi centers, what are the services that they found in the Anganwadi services? The first thing that we found, that they said that the Anganwadi centers are only open for 2 hours a day. Actually, it is supposed to be open for at least for 4 hours. So you find at least for 4 hours a day, that is only 9% of my surveyed, sampled caregivers. They reported that they found that it's open for 4 hours. And almost half of them said it's just open for 2 hours. Now, the Anganwadis discussed about the Anganwadi workers, AWW are the Anganwadi workers, discuss about the growth process of individual child to their mothers. Just barely 1/4. So what we suggested about the awareness creation, about the information given, that's only for the 1/4. And this 1/4, mind you, about those whose children come to the Anganwadi centers. There was a big chunk who never came, right? Now the Anganwadis discuss about the nutritional information to mothers. This is around 36%. Children receive regular eggs, 54%. This is again a shocking figure, because it is said that weekly, the norm is weekly, they should receive 2 days, they will receive eggs. But that roster is also not followed, it seems. No PSE reported. PSE is the preschool education. That is one of the services that Anganwadis are supposed to offer. It's 15%. And the quality of PSE good, see the percentage, 1.67%. Now, no TLM is used for PSE. So no teaching, learning materials are used, and the mothers' meetings are not regularly held. I will tell you that what we gathered during our primary survey. So when we went there, we found that one Anganwadi workers was writing on the board the word ball. So A for apple and B for ball. He had completely misspelled it, BOLL. Then we asked about, do you receive any TLM, the teaching learning materials? They opened a trunk. There, the teaching learning materials are very nicely kept. The drawing books, the colors, the posters, but they are never used. So when I asked them, why don't you use it? They said, then it will be worn out and people would not like that. So that's how we find. Now coming to the treatment variables. Now this is the one that children with access to ICDS, we find overall it was 48%. So less than 50% of the children had access to ICDS. And when I talk about access to ICDS, I mean that they actually they can go to the ICS. So they have gained the access. Percentage of children who go to the ICDS for last 6 months, because there was a critique that why the ICDS has not resulted in enough impact on the nutritional indicator, because we have taken a lot of children who have just joined ICDS. So the scope of improving has not been enough. So we have taken the children who go to the ICDS for last 6 months. Children who went to ICDS for 4 or more days in the preceding week. Sometimes the children are very irregular. So we wanted to know about this. Now, coming to the children whose mother received information about child nutrition, 17.95%. Percent of children whose mother received information about child's growth process from Anganwadi worker, 16.92%. And what is interesting in the last column, if you find, this is the chi-square statistic for district-wise difference. There is no difference except in the children who received eggs for more than 3 days a week. This was significantly different between Howrah and Uttar Dinajpur, because in Uttar Dinajpur, we find that only 1/3, less than 1/3 children reported that, whereas in Howrah, it was nearly 50%. So there, the difference was significant. In other ways, it was never significant. So that is the general story. And what we find that incidence of child stunting captured by HAS scores is also pretty high. 50% of our sampled household, when we captured, we calculated their heights and weights and used the Anthro software to find that their HAS scores have been below that what was needed. So 50%, more than 50% were actually stunted. And the incidence of severe malnourishment, which is SAM, captured by MWAC measurement, that was also 3%. So that was also quite high. What I would like to mention here, look at here that there is no difference. So therefore, the otherwise developed Howrah could not actually perform better compared to the relatively backward district of Uttar Dinajpur. Now, I will just briefly mention the results, because if you want to understand, it's a little bit of technical. So I will just point out that what was the difference when I'm comparing the impact assessment. So you just find out that when I am considering the children with access to ICDS, and I'm comparing with children who did not have access to ICDS, their HAS scores, the mean HAS score for the treated group and the mean HAS score for the control group, that actually is insignificant. And there is no significant difference in that. Similarly, these results did not find any significant difference because the T statistics was not significant. The T statistic came out to be significant only when the children who received eggs for more than 3 days a week. So that is significant. And children whose mother received information about child nutrition from Anganwadi. So that has the most critical difference. So the difference came out in terms of the issue that when the children are receiving SNP because they are coming to the Anganwadi center, but the mother is also receiving information about the child nutrition. Again, I would like to share the story that I faced when I was visiting the Anganwadi center. I had asked, I was looking at their graphs. You know, they have the graphs for each individual Anganwadi children who is going there. They have plotted graph that is mandatory for to prepare that. So I found that for a number of boys and girls, that graph is actually dipping. So from green zone, it is dipping to the orange zone and then to red zone, marking that they initially, when they started coming to the Anganwadi centers, they were actually in the green zone of nutrition. And then they're sleeping to the red zone. So I asked them, what's the law? Why this is happening? Have you asked? She said, no, I do not know, but that is what the graph says. So one of the caregivers of those children, she was there. She was the grandmother of that boy. So I talked to her and I asked her that, do you know that this is happening to your grandson? And she refused to accept. She said, what are you saying? I give my grandchildren the best of the food. In the morning, I give him a sumptuous breakfast. I said, like what? She said, I give them every day. This is in the urban part of Howrah, and this is a part of the Hindi-speaking belt in Howrah. And there are a lot of, on the pavements, and there are a lot of kachori, jalebi shops. So she showed me one shop nearby, and she said, every day I take my grandson because he is very fond of these kachoris, and he has these kachoris. And I also give them Horlicks. But I said that, do you know that this is happening to your grandson? She refused. And she said that, what else can I give? And then I asked the Anganwadi worker that, do you give any further information about what are the kind of nutritious food they can take at home? Because SNP is just one food. The rest of the foods are given at home. So wrong information, misinformation can actually nullify the positive effect of having good SNP at Anganwadi center. And the Anganwadi workers said no. So the takeaway from our study was, first, it is not just the breadth of the policy that matters, but the depth of the services would be improved simultaneously. So not just the people should go and be covered under one program, but also under that program, they should receive all the services. That is very important, because you see what we found here in Anganwadi, they get the SNP, but they do not get good PSE. They do not get more information, but they are a part of the basket of the services they are supposed to offer. Secondly, the ICDS program focuses solely on SNP, neglecting other components like PSE and awareness generation. Lack of quality of PSE, in fact, repeals the potential beneficiaries, because this setting is a rather food secure community where we had surveyed the most of the households were, however, food secure, where caregivers overwhelmingly opine that they have enough food for their children at home. When we ask them, why do you send them at Anganwadi centers? Do you have dearth of food? Do your children remain hungry at home? They said, no, we have enough food at home. So this is a kind of food secure kind of a setting. Thirdly, given the knowledge of large-scale protein energy deficiency among the Indian children, the importance of eggs in SNP is crucial. So it's not just the energy food that is important. You find that those who are receiving the eggs in the SNPs, they are actually doing better in terms of nutrition index. And further deep dive into analysis shows that as the number of supervision at the ICDS centers increases, the proportion of households receiving regular eggs also increases. Finally, the impact of simultaneous receipt of supplementary food and complementary nutritional education results in significant improvement in child growth process. And in short, the complementary programs of nutritional awareness and community-based food supply together appear to break the intractable barrier of child malnutrition in a developing but food secure setting in India. So that is the most important takeaway, I think, when we look at that in a food secure setting, a lot of people are actually, lot of children are actually malnourished. So the main issue is not just the supplementary food, but also improved awareness and community-based food supply. So both should come together, not just the SNP. So given this, I stop my presentation here and I look forward to some interesting discussion.
Thank you, ma'am. Thank you for the interesting session and informative session also. With your permission, I would like to start with the questions. Shall I, ma'am?
Yeah, yes, please.
Yes. Here is a question. We all know that the GDP of our country declined by 23.9% during this COVID-19 pandemic. On the other hand, there is a surge of advertisements regarding the immuno-boosting formulated foods all over the country. No doubt, these are too much costly compared to the conventional dishes of the average population. In the present circumstances, is there any future direction by which we can balance the economic crisis as well as the nutritional requirements?
Okay. Yes, the COVID situation has brought us all at a kind of a level playing field, and this is probably the biggest structural break in our lives. And it is true that India's GDP is shrinking, and which means people have less money in their hands to buy food. And hence, in this setting, the programs like this ICDS or the PDS, that is the food grain procurement schemes, they will be extremely important. And not only a targeted delivery of these things, but as I said, it's not just about giving some cooked food, a khichdi and half an egg to the children that will solve the problem. But there should be a bigger assessment, bigger information generation. And what we are finding that here, these immunoboosters, as you said, about everybody is asking them to take milk haldi, doodh haldi, and all these things, taking lemon, and these are there in our Ayurveda for ages, right? So of course there is a chance that we can revive this, but that should be done under a very, very scientific method. It should be coming out in terms of scientific research, because we so far do not have any direct scientific, overwhelming scientific methodology to find how the Ayurvedic medicines work in our body. So it's like it is there in our history, and we are getting advantage in this, but there should be more science-based, proper science-based treatments, and there should be more, more studies coming out that what are the things what we can do with from our everyday food or something like this. I'm sure that your faculty members who work with the physiology and with those medical parts of those parts can answer this question far better. But in terms of economics, I think that we cannot underestimate the involvement of the government, both state and central government, to providing not only the food, the SNP for the targeted population, but also creating a larger base of information.
Thank you, ma'am. The next question is, does nutrition play any significant role in poverty trap?
Of course, of course. Of course, because as I said that, that's what I said, that when it's the people become undernourished, undernourished. They cannot work. Their human capital is low because their learning ability is low. They cannot learn properly. They cannot go to the school and colleges regularly. So naturally, their learning capacity is low and their productivity is low. And hence, their capacity to earn income will be low in the long run. So there is a very strong relationship between low nutrition and poverty.
The next question is, how have you measured the quality of PSC?
That is the question. That was an open question that we asked. That there were options given in the Likert scale. That do you think the PSC quality was, how was the PSC quality for your child? Very good, good, average, bad, and very bad. So it was their perception of the caregivers. That is how we had measured.
Okay, ma'am. The last question is, due to COVID-19 lockdown, tribals and forest dwellers' livelihood had been affected, like collection, use and sale of minor forest products was not possible. This has led to several crises. Has the government taken any steps for addressing these issues?
This is not exactly related to nutrition policy, but see, the tribal people, particularly in Purulia, Jhargram, and the Jungle Mahal areas, yes, they are suffering a lot because their products are not being, marketed properly. And this is not just for the tribal people. The products that are being less marketed, yes, that's a problem everywhere. But given their lack of education and their lack of connection to the markets, they are more affected, you can say, because lockdown has created a lot of hampers in the entire supply chain. Any supply chain you look at, that has been very, very badly affected. If you look at the pharmaceutical supply chain, because most of our APIs were being imported from China. So that was affected, and we had lots of shortages in terms of that in the initial phases of lockdown. Now, since Indian pharmaceutical industry is a very, very capable industry, they actually worked well and started moving to create better, more APIs for ourselves. But the fact is that the supply chain has been completely disrupted. And that's true that since the forest dwellers are coming from a very, very distant, remote areas, they have actually suffered more, no doubt about it.
Okay, ma'am. There is another question. Do we need more qualitative studies or quantitative studies in the specific field of nutrition policy?
See, asking this question to an economist is like, this is, for me, I believe I work on quantitative economics and I use quantitative techniques, but saying this, I also do qualitative research, because in terms of quantitative research, we get to know the actual picture that what is happening. But when the question comes why it is happening, to insiders issue, sometimes we use methods and we go for qualitative research also. So, but quantitative research is the backbone. You will have to have. That's my opinion. Definitely, sociologists might differ because there is more qualitative answers to that. But being an economist, I would definitely prefer quantitative.
Ma'am, I have a question, please.
Yes, please.
Hello, ma'am. I have a question, please.
Go ahead.
Yes, ma'am. It's related to like nutrition in India. Like even though FSSAI has made it now mandatory to have this nutritional information on the packaging, packaged products, but still. Like in a country like ours, that is in India, where there are so many poor people, there are so many illiterate also, like the literacy rate is not that good in some of the states. So how will it be feasible to bring each and every individual to the level that yes, they know that we need this much of nourishment, and so that is my question, like how will be able to do it? We usually it is talked about undernourishment or overnourishment, but like how will it, how can we get this
That's
in
why
actual?
that's why I pointed out that it's not just about having or buying food and having it, but also you should have a kind of information about what kind of food is the best one suitable for you, and for that the Anganwadis can guide at the local level, and at the national level there are there are studies, and there are suggestions by medical associations, by ICMR, etc. And so it's more of a broad-based information. But if for individual at the rural level, definitely the Anganwadis can help, because if a child is severely stunted, they should give eggs to the child every day. So the diet changes according to the indicators, so they will have to learn about it.
Yeah, ma'am, just like the studies have been going on for past maybe few years, and also there has been awareness campaigns also. So, is there any improvement in the in this level? Like, is there any drop in the undernourished population in India, or like it's just
I
our
think I
studies only
cannot
going on?
see who is putting the question. I don't understand who is it. But the point is that there is definitely a reduction, but still the malnutrition is unacceptably high. And if you want to know about the statistics, please search the web a little more.
Okay, yeah, thank you, ma'am. Thank you.
Thank you, ma'am. I would like to request Purva Chattopadhyay, ma'am, to take over. Ma'am.
Okay. Dear audience, it is my earnest request, if you have any questions with the speakers, please type it in the chat box. And Orijita Di, thank you so much from the bottom of my heart and from the behalf of my department for being with us. And we are so proud of you doing such beautiful research and taking such a nice, giving such a lucid, nice lecture. Please continue your good work and enrich us with such beautiful discussions. So thank you so much.
Thank you, Purba, and thank you. My big thanks to the entire Home Science department. And it was actually nice to be a part of this. And as I said, I belong to the same family, so it was really nice to be a part of this international webinar as a part of the faculty of Calcutta University. And so I also enjoyed a lot, and I hope to get that I could actually give some direction of food for thought for your scholars and whoever is there. And if any of them have any specific query, please direct the queries to me
Sure.
through email.
Sure.
Thank you,
Sure.
Purva. And your
Thank you.
HOD ma'am is there. I should also personally thank her.
Yes, she was there.
Yes,
Okay.
thank you, Orijita, madam. And my wish is fulfilled.
Oh,
To
thank
put
you so much. That's
the,
good. The purpose is
to put
certain.
the two disciplines in the same platform. The interdisciplinary nature of nutrition and its relationship with economics, without which no nutrition is possible without economics.
Exactly. Thank you so
Thank you.
much. Okay. I take your permission. I'll leave.
Yeah, sure,
Thank you.
sure. Thank you. So, going on with the proceedings today. So our next speaker is again with us, and we are actually having quite a slice because not only our speakers are from different parts of the globe, but also the topic of discussions are so varied and wide that it is actually a very nice experience for all of us. So again, Debanjana, I would request you to come to the stage and please introduce our next speaker.
Thank you, ma'am.
Welcome,
Thank you.
sir.
Thank you. Is our next speaker here, ma'am? Ma'am?
Yes, yes.
Okay, ma'am.
Professor
Okay, okay. Thank you, ma'am.
Great.
Okay, so moving on to the next and final lecture session for today. With immense pleasure, I would like to invite our next speaker, Professor Mukund Karve. Sir, we are extremely fortunate to have you with us. Professor Karve has several accolades and accomplishments that are quite impossible to sum up in brief, yet I am trying my best due to the time crunch. Professor Mukund Karve is currently working as a professor and chair, Department of Food Science, Rutgers, the State University of New Jersey, USA. Over the last 22 years, Professor Karve's research has covered areas such as food extrusion, microwave and hybrid making, fortification of foods with omega-3 fatty acids, high-pressure food processing, and effect of processing on nutraceuticals in foods. In 2009, he was the recipient of William Cruess Award, the National Teaching Excellence Award in Food Science and Technology from the Institute of Food Technologists, USA. Professor Karve has published 124 journal articles with 2033 citations in the best scientific journals, along with his students and his collaborators. In the year 2019, Professor Karve published an article where a study was designed to experimentally investigate the influence of bolus viscosity on digestion and nutrient absorption processes. Using an in vitro gastrointestinal model, the TIM-1 system, two types of simple carbohydrates, namely glucose and maltodextrin, were used as model foods. Now, it is the moment to cherish the lecture by Professor Karve on the topic Modeling and Simulation of Transport Phenomena to understand the process of digestion in human GI tract. Audience, you are being requested to keep yourselves on mute and please type in your questions in the chat box. Welcome, sir. This is the moment that we have been waiting for. Please share your lecture with us.
Okay, can you hear me?
Yes, sir. You are audible.
Okay.
Thank you, sir.
Thank you very much. Thank you very much, Debanjana.
Thank you, sir.
Thank you. Good evening to everybody. Those who are in Calcutta and other areas, it's morning here. I'm in New Jersey. And thank you again for inviting me to this webinar. Thank you, Pabali. Thank you, Amita. And thank you all the organizers for organizing this event. And I will do my best to share what I work on, and hopefully there'll be questions that at the end I can answer. So let me see whether I can present, go to the present now. Let's see.
Thank you, sir, once again for joining with us.
Just give me a second. Here we are, present a window, present. All right. Can you see my slides?
Yes, sir. It is visible.
Okay. All right. Thank you again.
Thank you.
All right. So just a quick, can I start?
Yes, sir.
I can't hear you. Okay.
Yes, sir.
All right. If there is any problem, let me know. If you can't hear me or the slide is not visible, something goes wrong with the technology, let me know.
Yes, sir. Yes.
All right. So again, just a quick two slide introduction. I am from Rutgers University, one of the oldest universities in the US, more than 250 years old. And we are located on the East Coast. And the pictures here you see when President Obama came for our graduation ceremonies for the 250th anniversary. And the bottom left you see here is the discovery of streptomycin, the one that cured tuberculosis back then, was discovered on my campus from a soil bacteria. So that's our claim to fame. And like I said, we are very close to New York and Philadelphia on the East Coast of the United States. So that's where I'm located. So today I would make an attempt to talk about the mathematics and computer simulation of the transport phenomena to understand the process of human digestion in our GI tract. It's a very vast subject, as you all know. You are more familiar to it than I am, although over the period I have gathered some knowledge. I am primarily a mechanical engineer converted into a food scientist over the last 35, 40 years. So I try to use my engineering to understand the process of food science and nutrition as best as I can. So this is what I will talk about, the work done by my former student, J.S. Karthikeyan, and former postdoc Deepthi, who have now left, and they are working in industry and in universities as teachers. So I'll be sharing their work that they did while they were my students. So why do we need this research? Why do we need to understand and model the physics and the biophysics of the human digestion process? Well, there are a variety of reasons, and I can name many of them. But one of the reasons is that as the food processes goes through your alimentary canal, it is first broken down, which is purely a mechanical process, followed by the enzymatic actions of various enzymes. That's what happens in the digestive tract. So there's a lot of chemical engineering that goes on. And ultimately, the nutrients that are released are absorbed. So again, a lot of mass transfer and basically transport processes that occur that leads to what we call digestion. So one of the aspects, we can do many things from this modeling, but one of the aspects is to understand whether we can actually predict the rate at which calories are released or absorbed in the human GI tract. And can we ever control them? Can we ever control the release of them and predict them? And accordingly, we can design the foods for certain section of populations who might need quick source of energy or not so quick source of energy. If you are concerned with overweight or obesity, you don't want to raise your blood sugar or energy input too fast. So depending upon what you want, maybe we'll be able to control the rate of digestion through by controlling the physics and the chemistry of the process. And can we predict that so we can ultimately lead to the top level where we can design the foods and the recipes that will control that. So that's the idea, the broad picture, should I say. A lot of attempts have been made over the period of time, starting with human studies by feeding people certain diets and trying to measure their blood sugars and other components in the blood as a function of time, looking at effect of fibers and proteins and whatnot at the rate of absorption and weight gain and so on and so forth. These are difficult studies to do because of the variability involved from subject to subject, and expensive and time consuming. So it's very difficult to do in vivo methods until you have some understanding of what's going on. So that's why people have referred or resorted to in vitro models, where the other extreme, which is very different than what you see on the picture here. On the right-hand side, you see the whole complicated human GI system, and the extreme left, you see a reactor, which is where people started with, considering that the human system is like a reactor, which is in a broad picture correct, but there are lots there. When you look into the detail, there is a lot going on in the detail, but it's a good start. So people started by looking at nutrition as a reaction inside your system, and they started putting enzymes and whatnot into it and see how the food is digested. Now we have come far away that we can now take the next step where we can actually combine the in vitro system, which is more complicated than what you see in the picture, and mathematics or the modeling. Here you see a picture of stomach, or actually what we call as computational picture of human stomach, that we can now actually model the physics of that, of the process of digestion. So we have that is a much better, at least closer step to the real thing that goes on into the human system. And computers are allowing us to do that. So we have some prior knowledge that we can always build on. For example, almost 40 years ago, a paper was published by Kelly and others trying to understand exactly what happens to the particles, especially solid particles in the human stomach. And they found that most of the action that happens toward the end of the stomach, very close to the pylorus valve, where the intense mixing and the grinding of the particle takes place. And in fact, you get these particles that are ejected back and forth in this particular part of the stomach. This part of the stomach is mainly the storage and not really intense mixing. So that's the first idea that we got, that, okay, this is where the real action is happening in the human stomach. Later on, a lot of people have worked on it. For example, Professor Paul Singh at University of California, Davis, and his group and others have done a lot of work in terms of modeling human stomach in the details, looking at the peristalsis of the stomach, as you see on the right picture here, looking at various flows and velocities and shears and mixing that is caused by the peristalsis of the stomach. And people have gone on to looking at the mixing patterns and what happens to the particles and how they break down in the stomach because of the peristalsis and segmentation, which is nothing but wavy motions that are induced on the walls of the stomach to promote mixing and movement of the motion, movement of the food towards the pylorus valve. Eventually, the valve opens when the viscosity reaches certain low level and the food is released into duodenum. But that has been studied extensively by various groups around the world, particularly Paul Singh's group in California, and now some other groups in Kong's group in Georgia, and I'm sure there are others who have also looked at it. And very interesting findings that have come out in the past work from the mathematics, the numerical simulation of this work, basically something that you could have predicted, but that would have been just a guess. And now we have some mathematical evidence that the rate at which the stomach empties into duodenum, which is called the gastric emptying rate, is very much dependent on the viscosity of the gastric content. And you can actually change the viscosity by adding things like gums and fibers and other things that will control the viscosity of the bolus in your stomach. And therefore, the food will remain in your stomach longer because it takes longer time to break it down to reach a certain lower viscosity. And therefore, the feeling of satiation, satisfaction that you get is lasts much longer, and you feel less hungry quickly. So that is the idea. And again, the mathematics is shown here from Paul Singh's group, showing the strong jet-like phenomena that happens near the pylorus valve before it opens up. So the food comes down, and then is ejected back, then it comes down, then it's ejected back. And that's how the mixing and the particle size reduction and the soaking of the particles and the softening of the particles all happens in that action. And then people have now gone on to the next level. Again, this Kong and Singh, Kong happened to be the postdoc of Dr. Singh, has actually developed a large-scale model of stomach. You can see here it's only stomach, and by looking at the details of the walls and injection of various enzymes, he's looking at the actual model of the stomach. And then latest in this, as of last year, is the actual stomach developed. You can see in the left picture here with the fundus and proximal corpus and the lower corpus and the atrium and the pylorus valve, all made into a synthetic stomach, so to speak, that almost mimics the human stomach by actually putting the actuators on the stomach, and that actually push the walls of the stomach in and out periodically, just like the real human stomach. Electronically controlled with using solenoids and whatnot, and you can actually impose the peristalsis and the segmentations on the walls of this synthetic stomach and study what happens in the human stomach model without actually having to go to in vivo type of studies. And this is some of the pictures from the Kong's group, again, by looking into the details, how the segmentation can affect the mixing. Again, you can read these papers. That's not the idea. I'm not here to really describe the work of other people who have done a lot of good work, but I just wanted to build on that. So what they have found using gastric simulators, particularly stomach, again, like I said before, that viscosity is one of the primary factors that controls the gastric emptying rate. For example, they found brown rice is kept for a longer time in stomach compared to pure white rice, primarily because the viscosity is different. And then if you can control the viscosity by adding natural gums, such as guar gum or other gums, you can actually reduce the mass transfer coefficient of the absorption process and the transit times in the stomach. So that has been the findings so far. Still, there are a lot of unknowns. Like I said, the human studies to do these things that we can do outside in the in vitro models are very difficult, primarily because they're very expensive and very subject oriented. But bottom line is that we know almost surely that viscosity plays a very important role in affecting the residence time of the gastrointestinal content, and the whole digestive tract residence time is controlled by the viscosity and the rate at which the nutrients are released. And therefore, this is one of the primary parameters that we try to play with in our simulation and see whether it actually does something when it comes to release of nutrients in the gut. So my focus is not on stomach because other people have worked on stomach. My work is more on the small intestine, which is where it's relatively new. And my interest is trying to understand the fluid mechanics followed by the starch digestion and the glucose release in the human small intestine because of the motion that are imposed on the bolus as the food goes through the intestine. Once again, stomach, you can think of stomach as a bag with moving walls, and primary function of the stomach is mixing particle size breakdown with some enzyme actions happening. And ultimately, when the viscosity reaches certain low value, the pylorus valve opens and the food moves on to the duodenum. So my interest is in the next three sections of the small intestine, which is duodenum, jejunum, and ileum, which all consist together we call small intestine. And my focus is on the fluid flow, mixing, the reaction, the diffusion, and the absorptions at the wall, and see whether we can have any handle. Again, I realize this subject is very big and very vast, so I could be just scratching the surface, but you got to begin somewhere and slowly build on the model as we make progress. That's what I'm trying to do. So again, like I said, my focus is on duodenum, jejunum, and ileum, and the total length is about 3 to 4 meters long with an average diameter just over an inch, about 2.6, 2.7 centimeters. And depending upon the locations, different fluids are inserted in this tube, which is not a straight tube, very complicated shaped flexible wall tube, where biles and pancreatin and brush border enzymes are present. And as you go further down into the ileum, then there are villi and microvilli, and the surface area dramatically increases, and that's where the absorption of the carbohydrates and the amino acids and fat globules and whatnot happens. Again, I've started simple. I wanted to just look at carbohydrates, which are relatively simple molecule, not necessarily very simple, but relatively simple molecule. It's a major source of energy, as most of us know. Almost 40 to 50% of our diet is carbohydrates, and which is most of them are converted into glucose, which is what we need, and is absorbed eventually in the intestine and reaches our bloodstream. And that's why I started with starches and dextrins. And if this is successful, I will definitely move on to fats and proteins as we make progress through this endeavor of trying to understand the human gut flow through mathematics. So again, starch is broken down depending upon what kind of starch it is. Amylose, the branch polymer, amylopectin, the straight polymer, amylose, the straight polymer, the amylopectin, the branch polymer, and depending upon their molecular weight, and ultimately is broken down to, depending upon starting with mouth, with salivary amylase, to pancreatic amylase, to ultimately maltases that are eventually broken down to glucose as the molecules move through the system. And that is what we all know very well, which is what we call the glycemic index of the food. And this is what actually my dream is, to actually, if you give me the food in front of me and tell me its composition without eating, I can insert the composition and the recipe in my computer, and I will be able to predict, I should be able to predict the glycemic index of this food without ever having to consume the food. And if I could do that, I think it should be very useful. But that's where I'm heading to, is trying to predict glycemic index of the food from the composition of the food, the diet, and the person, of course. So all that's going to need a lot of factors coming into it as we move downstream. So we all know that. So that's what I'm trying to predict through the modeling. I fully understand that the real transport that happens in vivo, especially when it comes to glucose, is not so straightforward. As all of you know, those who are in nutritional biochemistry know this very well. It involves sodium and potassium channels transport that happens across the epithelial cells, and it is not such a straightforward phenomena. I am not trying to model this as a microscopic phenomenon. I am going to take this picture and average it out as an average diffusion coefficient for glucose across the intestinal wall, across the lumen from the left to the blood on the right-hand side, combining all these sodium and potassium channel transport into one or two terms rather than getting into the details. That would be the next step, logical next step, but not at this time. So again, the research goal was to see whether a given carbohydrate, can I control the glycemic index or predict the glycemic index if I know, or if I control the viscosity and therefore the absorption rate of the glucose in the intestine. So I had two-pronged approach to address this. One was in vitro experimental procedure, where we actually fed the food to a model which is very close to the human system, as close as it can get as of today, where we fed the bolus, the sugar or the starch solution to this in vitro human model, and then followed the bolus as it moved through the system and as affected by the viscosity of the bolus, and then looked at the rate of release of glucose in the jejunum and ileum primarily, because that's where most of the glucose is absorbed. Duodenum, it's not absorbed. Once we understood that, then we went to the mathematics of the process and see whether we can predict it and whether our predictions are anywhere similar to the actual thing that happens in vitro models. We don't have any data for in vivo human system yet, but hopefully we'll get there too in the next few years. Again, like I said, we use glucose-based system and a slightly more higher molecular weight maltodextrin systems under different viscosity changes in the GI tract, and looked at the process of digestion. So we made a simple glucose-based solution, very simple, 5 grams glucose dissolved in water. And then we mixed it with different liquids that had different proportions of glycerol and water. The assumption here was that glycerol will play very little role in the digestion. It will not interact with glucose. And the only thing the glycerol will do is change the viscosity of the bolus. And therefore, we can really change the viscosity substantially by changing the proportions of water and glycerol. And we did the experiment to make sure that we are getting the viscosity that we want. So by varying the proportions of glycerol to water, we could go from viscosity of approximately 1 millipascal second when there was no glycerol to almost 100. So we chose 3 solutions, 1, 15 approximately, and 100 as the 3 solutions of 3 different viscosities, which are, as you can see, varying by an order of magnitude by a factor of 10 approximately. And we mixed glucose and maltodextrins with these solutions, and then looked at the absorption of glucose release from these 3 different solutions. So how did we do it in the in vitro system? So on the left-hand side, you see the human actual system from mouth to esophagus to stomach to intestine, small and large. We have what we call as the intestine model, TIM. One being the version number 1. But it has various parts. For example, it has a stomach on the top, which actually has the mixing motion, where the food is introduced into the stomach and then it stays there, and it gets pumped back and forth like human stomach would do and then you can program it through a computer, and then you can release it to your duodenum, where the biles, the pig bile in this case, is introduced. The pH is maintained as close to the human pH, stomach in the human pH in the human stomach. Temperature is always maintained close to 37 degrees of the whole system. So we try to mimic as close to human conditions as possible. And then the food is programmed to pass on from duodenum to jejunum to ileum under pre-programmed conditions that we know from the human system studies, that how long it typically stays in duodenum and jejunum and ileum. And the rate of absorption of glucose is actually measured through a exchange across membranes, and it's like dialysis membrane, where we actually extract sugar from the system, and then undigested components are collected at the end, which is also interesting for studying further, because we can collect these undigested components, which could be dietary fibers and other things that we want to introduce into the next model, which we have it in a different system, which is the large intestine model, which is controlled by the gut microbiota and so on and so forth. So this does not have any microbes, although I'm aware that small intestine has small amount of microbes, nothing compared to the large intestine. But as of now, our small intestine model does not have any microbes in it. It's purely a mechanical chemical system as close to human system as possible. So this is the picture of that system. That was the drawing, and this is the picture. As you can see, this is the stomach part, which has two chambers, and the food goes back and forth between the two chambers until a certain amount of time, and then it's released through the system, and samples are collected at various points as you need them. This is very useful system, especially pharmaceutical companies are very interested in finding out when they design their medicines or the pills that they want controlled release delivery of drugs. This is very useful for them to as a first attempt before they start doing human system studies. So they regularly use this system to put their tablets in this and then see how different components of the tablets are released at different parts of the stomach, and they want to design their tablets so that certain medications are released only at a certain point when the pH is of certain level, and so on and so forth. So it's very useful system. Of course, it's also useful for human digestion system. So this is the TIM1 system that I was telling, and this is the program that basically is a standardized formula you can find in literature that allows you to predict at how the fraction of the meal is moved from one chamber to the other. This is not our formula. This is commonly accepted formula that is used in literature for controlling the transit time between different parts of the human GI system. So we actually fed the glucose and the maltodextrin based food into this stomach chamber, and then the total transit time for, in our case, from the point we introduced into the stomach till it came out on the other end was about 5 to 6 hours total, which is close to the human system. It is actual human system with solid foods can be a little longer, but ours was a more liquid system, so it makes sense to have a little shorter time. And then we actually collected the efflux from the jejunum and the ileum components, and it was collected periodically, and we then analyzed it for the glucose content as a function of time. So here is that typical glycemic index type of graph. Do you see when we fed glucose, and you could see the rate of absorption of glucose in the two components of the small intestine, jejunum and ileum, and you can see here that most of the glucose is absorbed in the earlier part of the small intestine, the jejunum. About one fourth approximately is absorbed in the later part of the ileum, small intestine, which is ileum. But surprisingly enough, which we didn't expect, but this is what the data is, and that for all three viscosities, 1, 15, and 100, there was no change in the release of glucose in the small intestine, whether it was jejunum or ileum. So that was first difference that we found that viscosity did not make any difference when it came to glucose absorption, because it was pure glucose. It did not need any further metabolism, no further kinetics was involved. And maybe that's why it did not have any effect of viscosity. So that's the conclusion. I just wrote it in Word. The glucose absorption was mostly in jejunum, and we could see that most of it was absorbed in jejunum, regardless of the viscosity, and very little went out as unabsorbed in the efflux. Then we switched to maltodextrin, which is a slightly more longer molecule, typically of the order of 15 to 20 glucose units that have to be broken down into individual glucose molecules by enzymes. And that's why it's expected to take longer to digest because of this, and the starch will take even longer. So we started with maltodextrin, and we again made a bolus of it. We again fed it into the glycerol water system with different combinations of glycerol to water to control the viscosity. And we fed it in the human system. And then we measured the glucose release in various components, same thing as we did before. Now, maltodextrin can be absorbed in different ways depending upon what their degree of polymerization is, and ultimately it will go out as a glucose, like I said, depending upon whether it's a branch polymers or the straight polymer. Ultimately, it will be released. So I don't want to waste time on that, but we collected the glucose that was inherently present along with the maltodextrin and the glucose that was ultimately converted after the complete digestion of maltodextrin. And that's what we call as base glucose and a total glucose, because we don't measure maltodextrins. We measure maltodextrin release in the bloodstream or in the efflux after converting them into the glucose unit, because that's an easy way to measure. And that's what actually we did. And again, what we found that when it comes to total glucose release from the maltodextrin, whether it's in jejunum or in ileum, no change. The total glucose release from maltodextrin was unaffected by the viscosity of the bolus in the small intestine, which was more surprising to us. But then we started digging deeper into it and trying to understand what is going on. And then we found the difference. And the difference came when we tried to break it down to where the glucose is coming from. And then we found, aha, there is a difference. That is, when the conversion of maltodextrin to glucose reaction is slowed down in presence of high viscosity, only up to a point. So for example, you see the blue curve and the red and the green curves. The red and green are again overlapping. So that means once the viscosity reaches certain level of 15 or 20 millipascals per second, we don't exactly know where that cutoff is because we didn't have continuous data, but we have only 3 points, but we guess it's somewhere around 15 to 20 millipascals per second. So if you have extremely watery bolus, then of course the glucose from maltodextrin is affected, absorbed very quickly. But if you have thicker bolus, then the conversion of maltodextrin to glucose is slowed down by a factor of 2 or 3 or something like that. And that is what came out of this research, a little bit digging deeper into it after going back and forth several times. When we saw this figure, we were surprised that nothing is changing. But when we dug deeper into it, we found that the reaction that converts maltodextrin to glucose actually has slowed down. And then we could see the difference of viscosity, effect of viscosity on the difference of conversion. And so that's the basic message here, is that the longer the molecule, the slower the digestion will be, the reaction in presence of higher viscosity up to a point. I don't think it will continuously increase, but up to a point, it will slow down in presence of more viscous material. So it tells you something, that if you can figure out a recipe of food in which you have components that are like hydrocolloid, that are like gums, such as carrageenans or something else, that will slow down the breakdown during the digestion process and maintain the viscosity all the way up to the small intestine. Then by doing that, you can reduce the rate of conversion of starch or maltodextrin to glucose, and therefore you can reduce the glycemic index of this by controlling the viscosity, by adding certain natural long polymeric molecules into your recipe. I just wanted to say on the side that we did actually measure the viscosity. I don't want to get into the details of that because that has been already published, and you can refer to the publication that was just recently talked about. But we did online monitoring of viscosity by putting probes in this system and using what we call as a fluorescence signal from a fast green, which is a molecule that fluoresces, and its fluorescence changes depending upon the viscosity, and we could actually measure that. Just we wanted to make sure that we are not just imagining that the viscosity is high or low or unchanged or changing just because we fed something viscous. We didn't know whether it has changed in the system, and it did change, as you can see, as the bolus goes down the system through the stomach to the intestine. The blue one being the no glycerol, then some glycerol and high glycerol. Eventually, by the time it ends in the small intestine, the viscosity is higher, but everything is broken down to a low viscosity material in our system. So glycerol is not a good idea to control the viscosity. Maybe we need to have some other molecules that can control the viscosity better. But that's a separate point. I don't want to dwell on that too long. Now, having done these experiments, when we predicted these curves, we wanted to see whether we can predict these curves through mathematical modeling and compare our predictions with this kind of data. So that's why we started developing into a mathematical model, which is primarily a fluid flow model, followed by the diffusion physics that happens across the walls of the small intestine. So without getting into too much of the mathematics and the details of numerical simulation, because it's irrelevant for this talk, but just to give you the background, we have a software called ComSol Multiphysics, which does not do modeling of the human intestine. You have to take this software and then apply it to your human intestine system in a way that makes sense. But the base program is there that can be tweaked and modified depending upon the physics of the problem, and that's what we did. We included the intestinal geometry and the motility parameters and the intestinal content properties, and tried to predict the motion as is imposed by the peristalsis. So here on the right hand side you see a very simple picture of peristalsis where the walls of the intestine contract. This is the same thing that happens in esophagus. It happens more or less similar thing in stomach, and also happens in the small intestine where the walls contract and the contraction move in a particular direction, and that's how the bolus moves to from one direction, in this case from left to right. And this is not a wave that keeps on going. The waves start with a deep wave and then it slowly dies down, but then a new wave starts. So that's why actually it's called peristalsis and segmentation combination that actually moves the food, the bolus, in this flexible wall tubing, if I could call it, which is intestine. So again, whenever you do mathematical modeling and numerical simulation of a real thing, you have to make certain approximations. So we assume that intestine is like a flexible tube, not a solid tube, but still it's a tube. And it's like a cylinder, and we assume that it's completely filled with food. We did not include the effect of gases in the small intestine, although there could be gases, gas pockets in the bolus and around the bolus, but that this time we have not included. And we have included the effect of peristalsis only, not segmentation. And our focus was on jejunum and ileum, because that is where most of the peristalsis induced flow and the absorption happens. And that's typically 120 centimeters of jejunum and about 180 centimeters of ileum. That is what we have simulated. And actually we wanted to see, I mean, how do we know what is this rate of pinching, if I could call it? How do we know we are imposing the right amount of pinching on the walls? So we went to the literature and we tried to dig out a paper, and luckily we found a paper by Okubo, who actually had taken an MRI scan of the human intestine here. And I don't know whether the animation will work, but I'll try. And you can see a little bit, at least. This is the small intestine all over the place, and you can see these peristaltic waves moving. So this group of researchers actually took several pictures and analyzed the data through the data analysis, and then um, they put together final picture as they best possibly could put in terms of the what happens for small intestines in terms of peristalsis, and they came out with this kind of diagram, which is pretty reasonable. Typical contraction cycle lasts about few seconds, 7 or 10 seconds, and the amplitude goes from about 18 millimeters when the tube is fully dilated, fully open, and it contracts quite a lot. From 18, it dilates all the way down to 4 millimeter. This is a significant contraction of your. So this picture that I showed is fairly reasonable. That the pinching is really significant. That happens when the walls of the intestine are pinched, and this wave is moves from left to right, and this is the actual data. As you can see, it's not a perfect wave, but that's a human system, and you don't expect perfect sine wave, but that's good enough for us to do some modeling based on this data that was. So we use this picture as our basis for the peristalsis, and then we took it from there and actually imposed it in our mathematical model. So again, we took that data, the average diameter about 18 millimeters with pinching going down all the way to 4 millimeters, which is about 78% contraction. And the periodicity of these waves of peristalsis is about 7 seconds. So here comes our mathematics. So if you could imagine for a second, the intestine is now vertical. So it's a long vertical tube. I'm only showing you a small part of that. And that's why these two broken lines tell you that I'm not showing the whole long thing. It will be impossible to show in one diagram. It will be a fine just line. So just to show the whole picture, I've broken it up halfway somewhere in the middle. And so the food enters from the duodenum from the bottom, and it goes out from the top. And this whole thing is combination of jejunum and ileum. And this wall you see right now appears to be a straight wall, but this is where the peristalsis happens and the food moves up. Without boring you with the mathematics, the peristalsis equation was developed based on the data, and this is the function that was imposed as a moving wall on this tube, and that allowed us to impose the contractions on the tube, as you will see in the next few pictures. And then you go back to a basic physics of conservation equations. I'm not going to bore you with this, but we use the standard momentum balance, energy balance, or mass balance equations, assuming properties of the bolus depending upon whether it's simple water or glycerol water mixture. And you can use a technique called finite volume method or finite element method to actually solve these equations. Without getting into details, I'm just going to give you the results, and we can predict the flow inside this tube. So again, this is the wall condition that we impose, and I'm sorry, I'm going the back direction. Here is the results, and you can see the peristalsis effect. The wave starts forming here, and the wave is pinching and pinching, and as the wave pinches, the material moves forward, but it's not simple pinching. The wave has a direction. The wave is slightly moving upward, typically about few millimeters per second on the wall, 3, 4, 5 millimeters per second, depending on where you are on this wave. But yeah, maximum velocity actually is 3 millimeters per second. And this wave is formed, and the wave moves up, and then the second wave moves up, and the third wave moves up, and that's how the material moves. And I'm just showing you a snapshot at different times, and that results in the bolus going from bottom to the top about 0.24, 0.3 millimeters per second, which is correct in terms of the total time spent in the small intestine, which is of the order of few hours. So if I could show you the animation here, I hope you can see the animation, the pinching of the walls and the movement of the food. You can't actually see the food moving, but if you do it over and over again for a longer time of few hours, eventually you will find the food is moving from bottom to the top at the same rate as you expect to happen in the actual human system. So this is just this one picture, but now you can imagine several of these happening on the walls of the intestine. So that was the first attempt to understand what we call the peristalsis imposed flow that moves the bolus from bottom to the top in the intestine. Now comes the next part. Okay, so this is just moving the food. So what? We want to know the absorption that happens on the wall. because it's not just the movement that we're interested. We want to know what happens at this wall, which is where the villi are and the microvilli are. Ultimately, outside this wall, where the molecules of the glucose are picked up by the bloodstream and taken to the circulation system. So we wanted to focus on that. So that's where what we call the diffusion model came into the picture. So we can imagine now this intestine in another cylinder, outer cylinder, which is where this absorbed glucose molecules are picked up. And so it's a cylinder inside a cylinder. So the food is this blue part, and what is released will be across the walls of these blue parts into this outer cylinder, which is taken away by the circulation system in the human body. And that's what we try to model. So again, this is just a tube, this is just the intestine, and this is the intestine with the outer tube. So this is where what we call AT is where the glucose molecules are picked up by the circulatory system and taken out into the human circulation. So we again, without getting into the physics too much, the mathematics of that, we again impose this peristaltic condition. You can see the flow occurring from bottom to the top because of the effect of the peristalsis. And then we included the physics of digestion of maltodextrin into the system. So we needed to know the reaction rates at which maltodextrin is converted into glucose because of the enzymes that are present. And so we had to use the kinetics of the amylase, the velocity, and the maximum concentration, if you're familiar with the kinetics of the enzyme reactions. And using that data, and we could actually model the conversion of maltodextrin into glucose. And so we did that. And then, like I said, we did not focus on the sodium-potassium channel transport, but we considered as a diffusive thin barrier across which the glucose diffuses or is transported from one side to the other. And this is something that could be useful for other people if they want to simplify the model. And that's what we were trying to do. So what we found that, again, I'll show you in the picture in 3 to 4 different graphs, cumulative glucose absorbed as a function of time when we had only fed glucose. And what we are trying to show here, without getting into the details, is the dark the blue dots are the experimental data about for the jejunum part, where the glucose absorbed experimentally measured. And the black line is the prediction of the mathematical model followed by numerical simulation about how the glucose is released in the jejunum. As you can see, most of the glucose, you can see the numbers, is released in the jejunum, and some is released in the ileum part of it. And again, we were able to reasonably well predicted how much is absorbed and at what rate, using what we call as the diffusion properties of this small intestine membrane, which we found out to be these 2 numbers. And somebody doing the mathematical model can find these numbers useful if they're not interested in doing the detailed sodium channel transport. And then we went on to do the maltodextrin modeling, the same thing. We included the kinetics of the maltodextrin digestion. And again, our numerical predictions shown by the black line and the black dotted line compared to the experimental data points. At least the trend-wise, it is similar. I would say it's not exactly one on top of each other, and I don't expect it considering the complexity of the system. But the trend-wise, at least, it's a good number and a good agreement. And we try to figure out what happens if if you can include just maltodextrin without any enzymes present in the brush border enzymes, as they're called, in the small intestine villi area. So when you add the brush border enzymes but no glycerol, you get the fastest rate of absorption of conversion of maltodextrin into glucose. Now, if you have no brush border enzymes and there is no glycerol, so still low viscosity, you get relatively lower. So you see here 4, absorption of 4, just remember that number, and it drops down to about 1.2 in absence of glycerol, in absence of brush border enzymes. And then you can further take steps whether you can add just the viscosity part by no brush border enzymes, but you can increase the viscosity by adding glycerol to about 15 millipascals per second, and you can further reduce the rate of absorption from 1.2 to about 0.8 or 0.7, something like that. So again, highlighting the point that when you increase the viscosity of the bolus, the conversion of microdextrin to glucose is slowed down up to a point. It doesn't keep on slowing down the more the viscosity it is, but as you go from 1 to 15, it slows down significantly, and when you go from 15 to 100, it doesn't slow down as much. The point is that we can predict this, and now we can extend this to larger molecules, more bigger than maltodextrin, as long as we know the kinetics of the enzymes that is responsible for breaking down the starch molecules into glucose molecules. So the summary of the numerical simulation part is that we can actually now impose moving boundary conditions, the peristalsis. We can make it more complicated, of course, by adding segmentation. The more the computer capacity you have, the more you can do. But at least now the physics has been incorporated in the numerical simulation model. We can make it more complicated for sure. This is just the beginning. And we can approximate the diffusion properties of glucose across the walls of jejunum and ileum, as you can see, as we found out from our experimental methods compared with numerical methods. So I will summarize here saying that, yes, the viscosity does play a role in the human digestive process up to a point. So far, based on our numbers, and we find that the viscosity is somewhere around 15. It could be 20 because we don't have continuous measurements, but certainly more than 15 for sure, where up to that point, we can control the digestion and the breakdown of starch-based molecules in the small intestine system. So that's one takeaway, if you want to take away, that yes, if you can control the viscosity of your product that remains viscous throughout the system and doesn't break it down due to enzymes and the pH in the human system, then you will definitely be able to control the release of sugar in the small intestine. And what we would like to do, of course, we would like to take it further to make complex carbohydrates into the system, starting with long chain starch molecules of amylose and amylopectin, followed by even more. And eventually, I would like to get into the digestion of fats and proteins, and then look at the effect of thickening agents other than glycerols to see what happens in presence of those long hydrocolloid molecules in the system. Numerically, we can do a lot. Once you have a computer model, that's the beauty of computer model. Once you know it is working correctly, then it's easy to play with it. To get to that point takes a long time. And you always never know whether what you're predicting is correct. So you always have to have experimental data as best as you possibly can. And that's why I don't like to do only numerical simulation. I always like to have some experimental backing to at least get an idea that we are not completely moving in the direction that may not be correct. So I think this is the first step towards a much larger project of trying to understand the digestion by controlling the recipe and the viscosity of the product. I'm sure you can control other things too, particle size, shapes of the particle. Many people are working in that area, showing how particle size and the shapes and the internal structure of the particle also slows down the reaction rate. So that can be also included in the modeling. So the idea is to ultimately relate it to a product that you're going to make in a plant. So you can supply this information to the manufacturer so they can design the product based on whether you want to slow down the caloric intake or we want to accelerate the caloric intake. Depends what you want. You can design the food based on this understanding. That's my hope. And my ultimate goal, I don't know whether I'll achieve, most likely not in my lifetime, but this will be my dream, and you have to dream big so you can get there, is that if you give me a food product with a given composition and how it was manufactured and who is going to eat it, all I need that information. I go to my computer, feed that data. Maybe I need big data and AI in combination with a numerical simulation model. And without feeding it to actual human, I will be able to predict a glycemic index, what is called a lipemic index, which is basically at what rate your triglycerides go up in your blood, and maybe other nutrients, whether it's calcium molecules or some vitamin D molecules or whatever it is that you may be interested in. I want to be able to do this sitting in my office in a computer, in front of a large computer. Uh, you give me the composition, give me the manufacturing process, tell me who is going to eat it, and I will tell you what's going to be its lipemic index and the glycemic index. That's my dream. I know you might think I'm crazy, but this is how I'd like to imagine and move in that direction. So that's what I hopefully will make some progress in my lifetime at least. So, and then of course, there's another huge topic that I'm interested in is the modeling of gut microbiota and interactions that happen, which is even more complicated than what I presented, because the number of bacteria in the gut are billions and billions. So you're going to need a large system modeling technologies, methods that deal with large numbers and things like that. So that's very interesting, where I can combine AI with big data to understand the gut microbiota and its impact on the human health. That's even further down, but I've started thinking about that, how I'm going to do this and what needs to be done. So all this work was done because of my students and postdocs and the help that I received from various people in my department and support I received from my university and the departments and the graduate students, without which this work would not have been possible. So I appreciate their contributions and thank them for their work. And thank you for your attention. Dhanyawad.
Thank you, sir. Thank you so much for this enlightening session. We have some questions here. With your permission, I would like to proceed.
Sure.
Okay, sir. The first question is, what is the effect of adding probiotics in large intestine?
Probiotic. Oh, that's a whole different volume. You're asking a question that not really related to my topic. Okay, but probiotics. Oh, that. So probiotics are the one. Probiotics are actually the bacteria. You're not talking about prebiotics, right? You're talking about probiotics.
Yes.
Yeah, it will definitely change the gut composition and the interaction of food. And we have actually people working in my university. I'll give you an example. You'll be surprised. There is a professor who actually changed the gut microbiota in his intestine by actually injecting a completely different gut microbiota externally and change his gut microbiota in his system. And he went, without taking the name because I don't have permission to take his name, but the person actually lost significant amount of weight and is able to maintain that weight doing normal lifestyle. I mean, same dietary pattern, but because of gut microbiota, he's published a paper on that. If anybody's interested, I'll be very happy to share it. It's a very popular paper in Nature, I think, if I remember, but I can share that paper.
Okay, thank you, sir. The next question is, can you please highlight on the working of this model in diseased conditions of small intestine?
I mean, if there is a blockage, something like that, yes, we can simulate that. Absolutely, we can simulate that. I mean, one of the disease categories I know is intestinal blockage, or maybe somebody has some disease like a Crohn's disease that affects primarily the small intestine. Yes, we can do it, but without help of a doctor who can actually give me the information, like I got the information from the doctor about the peristalsis, I can't really model it. I can't predict without seeing what's going to happen. But if I have any idea how the intestine is affected by the disease, then I can predict its impact on the digestion process.
Okay, thank you, sir. The next question is, if we add lipids in the system, what can be the effect?
If we add what?
Lipids, sir. It's lipid.
Oh, lipids. Oh, so lipids have a different altogether, as you know, digestion genetics. Lipids come in these globules, as you know, small droplets, fat globules, and I will have to get into the modeling will have to be changed because lipids are usually in the droplet form. So therefore, I will have to use multi-phase modeling, where I have droplets of lipids surrounded by the bolus liquid, and how these fatty acids. The model will change substantially if I have to include lipids, for sure, because that will include droplet dynamics too.
Okay, so The next question is, if we want to work with nanoemulsion digestion in simulated gastric and intestinal condition, can we use POM-SOL for the numerical data, where nanoemulsion is composed of lipid, phospholipid, and water?
Yes, you can. Absolutely. The model size will just go very big, so I probably will need a supercomputer to model. But in theory, yes, you can do it.
Okay. The next question is, have you used sodium channel transporter to measure the diffusion of glucose in mathematical model?
Not yet, not yet. But thank you for the suggestion. Not yet.
Okay, thank you, sir. Next question, sir, do you think that the future direction of nutrition and diet therapy to reduce the calorie absorption and to mitigate obesity should be based not only the glycemic index of food but also the viscosity? Shall I
Maybe I didn't
repeat
hear
the
it.
question?
Yeah,
Okay.
please repeat.
Yes, sir. Do you think that the future direction of nutrition and diet therapy to reduce the calorie absorption and to mitigate obesity should be based not only on the glycemic index of the food but also on the viscosity?
Yeah, I think so too. But I think the other suggestion that came, in fact, some research that was done in our lab by another professor showed, in fact, that nanoemulsions may not be desirable when it comes to fat molecules. In fact, as they found that homogenization of milk, where the fat molecules are reduced in particle size, actually increases the blood lipemic index much faster. So you may not want to reduce the particle size of fat molecules if you want to reduce the rate of absorption of fat in the intestine. It's a counterintuitive thing that you may not want it. So there is a downside, actually, I found out that homogenization and all these technologies that are used for milk actually have a detrimental effect when it comes to fat absorption.
Okay, sir. The next question is there any relationship with amount of lipid in the diet with absorption and metabolism as well?
Some parts are missing when you speak, so say it again, please.
Okay. Is there any relationship lipid in the diet with absorption and metabolism as well?
I don't know the answer to that question, but maybe there is. I really don't know.
Okay, sir. Last question is, intestine is very complex system. How can we compare the data with in vitro system?
I agree with you 100%. It's extremely complex system. So that's why we went from a beaker-like in vitro system to the next best possible, where we have now flexible tubes that is closer to with the peristalsis on it. It's still not exactly like human intestine, absolutely right, but it's in the step in the right direction. I agree with you 100%. We need to have now the next model that is even closer to the human intestine. And ultimately, the final proof of the pudding is animal studies and human studies. But those are extremely expensive. So as you know, those who have worked in that area, and they are subjective, which is part of the problem and part of the solution. But I think the TIM model is the best approximation you can get between a beaker and the human system. And yes, I agree. I wish I had better, but this is the best we have as of now.
Debanjana, I take this opportunity to communicate with Professor Harvey, because I have gone through his work. It's a very nice presentation, and the work is, I can't express how much I loved it. Because I also work in the modeling. I don't work in the modeling system, but we have worked with the delivery system in the
Right.
in the everted SAC model. We have used everted SAC model and another system in in-situ model, where we experimentally found that there are some effects of the probiotics of the bacteria present on the surface of the intestine. And they change the, at I'm communicating with you that what we have found in our the lipid molecule, and they keep on lipid molecules. They produce some short chain fatty acids that are very helpful for immunity. And these are absorbed in the basolateral side of the enterocyte. Enterocytes are very important part of this model because these enterocytes have two walls at the basolateral side and the apical side. And all the transporters that are present in the apical side are not present in basolateral. And they have different affinity for the different molecules. So sometimes the molecules enter the system, that is the lacunae, and then again the enterocytes they absorb to the basolateral side, and the enterocytes metabolize within the enterocyte. So it's a very complicated system because when you come with the microbes and the hormones also, because in the system there are many hormones and all these movements that the movements are totally controlled by the local hormones, and I think and they are different from one person to other, and that I don't know how all these factors will come into your body system, because that is very important for moving towards perfection. Because as you will take more and more the factors into account, you will go towards perfection, towards the ultimate. It's my view in your work that biology is there will be more biology, addition of more biological parameters, because diffusion is very low with glucose in the real system, because most of the sodium channels, the sodium transporters, sodium dependent glucose transporters, they are highly concentrated in the intestine. And, they have to be taken into account, I think.
Pardon, ma'am. Pardon, ma'am. Oh, your sound is echoing.
Lot of echo.
Yes, ma'am.
Yeah, I got the
please.
point. I agree with you. I think I got the point. I agree that I said in my presentation that eventually I would like to get into the sodium channel transport and the gut microbiota, which was not at all part of the small intestine. But yes, I think what you said is absolutely right. Those are very important, and that is probably going to need a slightly different modeling approach, because like somebody mentioned in the message, we probably need to bring in the big data and the AI type of modeling also combined with this kind of modeling. So it's a big project, and that's what makes it interesting. But we've just started in that direction. It's going to take a long time to get there, but we'll get there. But thank you for the suggestions. Those are correct. All you said, everything what you said is right.
A wonderful lecture. I can't express how much it amazed me. Thank you very much.
You're welcome. Thank you.
Thank you, sir, for this wonderful presentation. I would like to request Dr. Purva Chattopadhyay, ma'am, to take over, please.
So what an experience listening to this wonderful lecture. It was actually a flow through which we could just go through the wonderful research, the unique kind of research that you are doing. Thank you so much for sharing your experience and research with us, sir. And on behalf of the Department of Home Science and from all the faculty members, we wish you all the best for the future endeavors.
Thank you very much. I appreciate all the comments and the questions. Very good questions, very relevant questions, and I learned something. Thank you very much.
Thank you, sir. So with sir's wonderful lecture, Today our session comes to an end. So tomorrow our session is the morning session, and we will meet again at 9 o'clock.
Okay. Good night, everybody.
Good night,
Bye-bye.
sir. Bye, sir.